I just did. Okay. Whenever you see this going, that means the recorder is recording. If that's not counting off, it's not recording. So what you see here under the YouTube video content is the old stuff at the top, the new stuff at the bottom. Okay? And let me get your name. Second. Donald, got it. Okay? And Mercury, got it. There you are. And you were marked present in the first class, in Thursday's class. I went back and checked. You were marked here. I'm sorry?
It said that on students' week. Did you mark yes?
It still says that?
I haven't checked it.
Well, it was. I went in and checked after you told me that, and you were marked present. Yeah. So, yeah. All right. Now, I'm showing the new students here how you access YouTube videos, and again, the current things will be at the bottom. Now, what I didn't describe before, because I forgot to do this, I'm recording this using Screencast-O-Matic. That's what's being recorded here. And when the class is over, then I will send this to YouTube. When it finally loads on YouTube, which will probably be sometime tomorrow morning, it'll probably load sooner than that, but I won't be able to. It will be sometime tonight, and I'm not going to stay up and do it. But when I get it into the playlist, then after that you'll be able to see it by clicking on what we just did. Rihanna, got it. Okay. And someone, the food smells good. Okay. And what's your name, please?
Justin.
Huh?
Justin.
Justin, got it. Okay. I have a good memory. It's just short. There you are. Okay. Has anyone else come in that I didn't acknowledge your name? Okay. Okay. So that's how you can catch up everything we did on Thursday. Go to the bottom of this and click on the one that says syllabus. Like I said, there's a lot more than syllabus there. Now, like I said, we got about halfway through the first chapter. So I'm going to go and get out of this and show you what else is here. All right. Now, like I said, this symbol means document. This symbol means web link. That's why you click on that and go straight to it. This one means a folder. Now, the folders also have, yes?
How did you go back to that right there?
Okay. Usually the blue X at the top. If you do here, it takes you back to the first thing, but usually that's how you go back to the previous screen. Okay? So, this is a folder. It's a folder of 10 beautiful photographs taken by the Hubble Space Telescope. You don't need to know anything about them. It's not necessary, but they're just really pretty pictures. A student sent them to me. They were really neat, so I put them out there for everybody else. Here's another document, Space Objects in Perspective. Really interesting, page after page, looking at relative sizes of various objects in space. And the scale is amazing, absolutely amazing. And then here we have another folder, and in the folder is the PowerPoints. And I was going to show you here, if you open this, you open the folder, supposedly. Why isn't that opening? There they are. And they have weird titles and things like that, but those are those 10 beautiful photographs taken by the Hubble Space Telescope. All right. I usually close this because they take up so much room. All right. There's a space object in perspective. That's a file. And here's their PowerPoints. Now, the PowerPoints they're big PowerPoint files, one for each chapter. Okay? And there's chapter 14, 15, 16, 17. Why it's not advancing, I don't know. 18, 19, 20. We skip 21 and 22, and then have 23 and 24. So those are all the PowerPoints we have. These are in static form. However, if you go to the YouTube videos, you don't just see the PowerPoint, you hear me talk about them and sometimes write on them. So you get to see a lot more through the YouTube videos. But this is a static form. If you want to print them out or look at them before we do them in class, that's perfectly fine. I'm just going to close the folder, and it's closed again. All right, so that's how you access Blackboard. That's how you pick up anything you may have missed in the first class. All of it's there. Okay. Now I'm going to get out of this unless there's some questions. Are there any questions about Blackboard? Any? Okay.
Did you put a test out there?
Did I what?
Put a test out.
A test?
You didn't do anything yet.
No.
Last week.
Generally, I don't put tests out there. We have tests in class. Yeah. Okay. Now, see the blue box with the X in it? When I click on that, I leave the Physical Science 111 and go back to, well, I think I do anyway, back to all the listing of my classes. So usually the blue box at the side is what you do. And this is, I know who you are, David, right?
Yes.
All right. Anyone else come in since I called roll? All right. Now, I won't do anything else on Blackboard unless there are questions about it. Are there? Good questions so far. Excellent questions. All right, so I'm going to get out of this, and now let's get back to the actual class. We're going to pick up where we left off last time, and that's from the current slide. Okay, supposedly it's going to go to the current slide, but so far it's not, so let me try it one more time. From current, yes. I'm sorry?
Are they on Blackboard?
What on Blackboard? The PowerPoint, yeah. That last folder that I showed had all the PowerPoints. Okay. Now, we already talked about this slide last time, and this slide is on page, if you got the book, okay, there's two types of books. There's the big, thick, heavy one that they don't sell in the bookstore, but you may pick one up from someone you've known or had it or whatever. This is on page 359. If you have the one in the bookstore, they may renumber or they may have both sets of numbers. But this is under star temperature, okay, on page 359. And then that was the graph on page 359. And there's the table that's on page 360. That's where we ended last time. Now, where do we go from here? From now on, we're going to pick up where we left off in chapter 14, and my guess, and I believe I'm pretty correct on this, we're going to finish the chapter today. Okay. Now, I think it'll be well before the 3:45, which is our first break point. Well, a break point. So what we'll do after that is move on to chapter 15. Okay? So that's what we'll do. But when 3:45 gets here, we will stop wherever we are in chapter 15, and we may have a little break, and then I've got the labs run off. We're going to do the lab for chapter 14. I always do the labs at the end, so if you finish early, you get to leave. If we did the lab right after the chapter, then we have to wait till everybody finishes the lab and then pick up again, and you don't get to leave early. So this way, if you finish early, you get to leave early. Okay. Now, let's look ahead into the future. On Thursday, we'll continue chapter 15. If we finish that chapter in the first 2 hours, not 2 hours and a half, but 2 hours on Thursday, then we'll go on and have the lab for chapter 15. Okay? If we don't finish the chapter in those 2 hours, we'll go on and finish the chapter and then start chapter 16 and then have the lab next Tuesday. But the last 30 minutes of Thursday's class, this Thursday's class, will be the test for chapter 14. Now, I understand that some of you don't have books yet in the bookstore. They hadn't ordered enough. Okay, sorry about that. If you want to wait until you actually get your books to take your first test, you can. But you'll need to come in during my office hours and take it. And remember, on my Tuesdays and Thursdays, I have very limited office hours. But you're welcome to come in and take it. I might be teaching another class, and I'll put you in a room next door or something like that, and you can take it then. But on Tuesday and Thursday, I have an 8:30 class, a 10 o'clock class, 11:30 class, and then this class starts at 1:15. So, and then we go till 3:45, so 5:45. So it's stacked days. Now my Mondays and Wednesdays, a lot more office hours there, 8 to 10 both days, and on Monday also 3:45 to 6. My Fridays, usually I have office hours on the Birmingham West Campus from 8 to 12, when they don't call meetings. But this Friday, I won't be there. I've got to go out of town, so I will not be there this Friday. Okay. So if you don't feel ready for the test on Thursday, and we will, if I finish the chapter today, which I think I will, then the test will be on Thursday. You want to wait until you get your book and are able to read the chapters and stuff, that's fine. But just get it made up as soon as you can. Is that all right? Everybody okay with that? You'll need to see me during office hours to make it up then. Okay. Now, this also sometimes happens. It sometimes happens we may finish a lab a bit early, and therefore you may have time at the end of that class to make up a test. So it doesn't have to be an official office hours, that could be then. Or we may have a lab followed by a test, and both of them, neither one of them take as long as scheduled. You may have even more time. Yeah.
What is your first test?
The first test will be Thursday. The last 30 minutes on Thursday. Chapter 14. Yeah. So by all means, go back and see the YouTube video. You can sit through all the other parts if you want to, but especially where it picks up on the chapter 14. And I think you can see that fairly easily. Y'all know how to manipulate and navigate through websites. Yeah. Oh, yes. Okay. This is, I guess, a legitimate question. There is a lab manual, but I've decided at the first time I taught the course not to make you buy that. It just seemed wasted. So I usually will copy the labs out of the lab manual and pass them out to you. Here is a copy of it. And if you remember, earlier in this chapter, we were talking about the celestial sphere and celestial coordinates. That's what the lab will be today. So, and we'll do it as a one group. Everybody will do. Now, I have a couple devices that y'all will actually be looking up and finding stars and constellations using that device. Nothing very difficult. We'll go through it together. Everybody will do it. We'll also do a few simple calculations, mostly adding, subtracting, that kind of stuff. And so this is the lab. Hopefully we'll get it done in 2 hours a day. If it takes us a little longer, then we'll use the first part of Thursday's class to finish this lab. Okay? Does that answer enough? Okay.
We use the lab. I think it's dissecting.
Okay. We'll be dissecting stars. Okay, yeah, okay. We'll lay them out on the table and cut them apart. Okay. Now, any other questions? Good questions, by the way, folks. Okay. Now, let's do where we left off last time was on page 360. It's an example 14.4. Now, again, a lot of these examples are based on stuff that happened in the first half of the book, and since y'all haven't had the first half of the book, we won't do too much of them, but I did want to at least give you a flavor for what they're like. Now, what I have to do is find, there's some gray space that I can do example 14.4 on. It says, what is the temperature of a star emitting light with a peak wavelength of 3,500 angstroms? Okay, actually, let's do this one. What is the temperature? Let me get my pen set up. Of a star my writing stinks. Have you ever signed out of Home Depot or somewhere with these ionizing pens? Did that look anything like your signature? Okay, me too. Okay, so sorry about the writing there. These are a little better than those, but they still. of a star emitting light with a peak wavelength of 3,500 angstrom. Of a star emitting light with peak wavelength of 3,500 angstrom. Now, y'all don't know what an angstrom is, probably. It's just a measure of length. Very, very, very short lengths, okay? If you can see, there's maybe a little space between my finger and thumb. That'd be many hundreds of thousands of angstroms. Really small. Yes? I'm sorry? I can't hear you. It's up to you. I don't.
What was the A?
What's that?
The A. What was it?
It stands for angstroms. It's a
Angstrom?
angstroms. Yeah, it's a very small unit of measure. Okay, very, very small. Approximately the distance between atoms. That small. Really, really tiny. Okay. Now, the reason I put this back up is the peak is 3,500 angstrom. That'd be somewhere here. That would be in the ultraviolet range, it looks like to me. Because violet starts there at 4,000. 3,500 would be somewhere there. Okay? Now, I left off my comma. Now, right before this, they had a formula. I didn't mention the formula. It didn't show up on the slide, so I forgot about it. That says temperature is equal to 2,800, no, I'm sorry, 2.8 97 times 10. That is a bizarre way to write this. Kelvin, that's a degree measure, angstroms, now I put the abbreviation here, divided by this symbol. That symbol, even, it doesn't have that many curly Q's on it. It looks like a stick man with no arms or something like that. That is the symbol for wavelength. It's a lambda in the Greek alphabet. Yes.
What is it called? A plank?
I'm sorry?
What is it called? Assembly.
Lambda.
Lambda?
Lambda. L-A-M-B-D-A. It's the lowercase letter L in the Greek alphabet. That's lambda.
Can you rewrite it?
What's that?
I said, can you rewrite it?
You said that's
2.897 times 10, which is a strange way to write this, K angstroms. Okay? This is the K is temperature Kelvin, and angstrom is a length measure. Like I said, it's an unusual formula. That's why I tend not to deal with it because it's just really strange. Okay? Now, and this is lambda, which is the wavelength, and that's the peak wavelength. Okay, that symbol lambda means wavelength, and this is the peak wavelength. Okay, so from what they gave us, this is your lambda. Okay, lambda peak is equal to this. Okay, so what we do is plug in, this is why I tended not to want to do this, 2.897, and why in the world didn't they just make it 28.97? Because times 10 would just be multiplied by 10. So 28.97 Kelvin angstroms divided by 3,500 angstrom. And notice the angstrom units cancel out. And you're left with Kelvin, which is how hot it is. That's your peak temperature. So, the only problem is I don't believe they're using, and this is why I usually tend to ignore this one. Oh, I see what the problem is. Sorry. They wrote it wrong. I'm sorry. I thought this isn't making any sense. I'm going to change this. Okay. I thought this is the strangest way I've ever seen this written. That should be 2.897 times 10 to the 7th. That's an exponent, 7th Kelvin angstroms. So this will be 2.897 times 10 to the 7th Kelvin angstroms. Okay. So, what you do to figure out what temperature this is, now, most of you have a calculator or at least a phone or something you can do the calculation. Do you have scientific notation on that device, whatever device you have? Do you know if you do? Okay. See if you see a key there that says EE or EXP. One of those two keys, EE or EXP. If you don't know, I'll be glad to come look for it. See if you can find it. EE, capital E, or EXP. EE, fantastic. Does everybody else find that key? Here's how you use your scientific calculator to do that. You type in 2.897. Don't do times 10. Do your EE or EXP key, right? That takes the place of times 10. And when you type that in, you'll see another little block show up. Type in your 7 there. Okay, then do your division symbol, divided by 3,500. 3500.
So we're looking at 10.000069.037.
Okay. Did you just give an answer? I couldn't hear what you said.
I said 10.000069.037.
Okay, you said 10 point
0.00069.037.
37. That doesn't seem right. Okay, and here's why. Because this is times 10 to the 7th. This is times 10 to the 3rd. And if you moved it here, it'd be 10 to the 4th. So that number doesn't seem at all right.
Let's go over it again.
Okay, 2.897. Then press the EE key. So again?
It gave me a -1 when I did that.
When you did EE,
Uh-huh.
okay, and then you type in a 7
Got a 7.
and divide it by 3500. Equal.
You got 10 points.
Okay. Let me watch you do it. And you had your hand up too. You want me to?
I was just trying to get better understanding of what.
Okay, wait. Let me watch it. EE. Wait. No. Okay. Now, what you did is okay. Start up. Okay. Now the EE is a second. You see, it's in the right like that. Second, and then that. Now that's where you put in 7. Divided by, and then the 3,500. Yeah. 8,287 or something like that. Okay. Is this 3,500? Yeah. There may be round off error. Okay. Did you have a question?
I did hit the 2nd button.
Oh, okay. I can understand which one.
Okay. Here was the problem. It said, what is the temperature of a star emitting light with a peak wavelength of 3,500 angstroms. Okay? Say again? No. Okay. This is just to give you an idea of what we're dealing with here. Okay? So here's the formula for it. T is equal to this number. They left off the 7. That's what was confusing. Dividing by the peak wavelength. Well, here's the peak wavelength. They just said peak wavelength of this. So you take this number and divide it by this number. And when you do that, you get something on the order of, let me correct this. Okay, and tell me what that was again? Approximately. You who puts it in? 8,200? Is that what you said? 277. Somewhere in that ballpark. Okay? Now, it says what's the temperature? And that would be Kelvin, because you had that unit left over, Kelvin. And that's something between this one and that one. What that communicates to me is that our graph isn't too accurate here. Because I was saying this should be somewhere out here. This is saying it's somewhere between 6 and 10,000, 8,000 between that. It would be somewhere about here. Okay? So, again, their graph is not, I was going to try to estimate it from here, but that's not a good estimate. This gives you the answer. Let's see what they got in the book. They rounded it at 8.3 times 10 to the, you moved it 3 places to the left, 10 to the third K. That's the temperature. All right. I'm regretting we ever did that. Okay. But it just, that graph obviously is not quite precise, because I would have said it would be in here somewhere. It's saying it's somewhere in here, okay? Between that peak and that peak, somewhere in there. Because it's 8,300 approximately Kelvin. So somewhere in between. Now, the next one, example 14.5. Okay. I'll erase this. In fact, I'm going to, since that, wasn't very accurate, I'm not going to use that. Okay. A star emits light with a peak wavelength. So here's our lambda peak. Lambda stands for wavelength. L, lambda, length, of, this is 8,500 angstrom. Okay. What is this star's temperature? Its color and its type. Okay. So we've got 3 answers there, or 3 questions. What is the temperature? Say again? Yeah, 8,500. Okay. What is the temperature? What is the color? And what is the type? Okay. Now, the temperature we got just like we did before. That formula was temperature is equal to 2.897 times 10 to the 7th Kelvin angstroms. Okay. And I'm going to go on and change that in my book, because that drives me nuts that they didn't put the exponent there. Okay. Divided by the lambda peak, which is 8,500 angstroms. And by the way, if you go back and look at this one, 8,500 angstrom would be somewhere down in the between 7,000 and 10,000. Theirs would be 8,000 here. So it looks like you're into infrared, but that I don't think that's very accurate. So that's why I'm not going to use that. But you're well farther to the right. Okay? So let's do the math. 2.897 EE or EXP 7 divided by 8,500. Someone give me a number. 3,408. Okay. And they say 3.4 times 10 to the third. Okay. This would be Kelvin, which they're rounding to 3.4 times 10 to the third Kelvin. Okay. So let's go back and look at our chart again. Here is 3,000 Kelvin here. Be just a little bit beyond that. It looks like to me the color would be sort of orangey. Okay? Now, if you look at the table down here, what do we say, 3,400? That would be just below that. So they call it reddish. I said orangey, but they call it reddish. And if it's reddish, that's, so there's all three of our answers there. You calculate this one, 3.4 or 3,400 Kelvin. Here was the temperature between 2,000 and 3,500, so just below this. And that's a reddish star, so there's this is the first answer. Here's the second answer. What type? The very coolest of your stars. Still awfully hot, but very coolest of the stars. Okay? That's how you use the tables, the charts, and the other things like that. Okay. The main thing to remember here, what is good old sun? Where is the sun in this picture?
In the middle.
Second?
In the middle.
Kind of in the middle. Can you tell me a little more specifically than that? As in, whoa. Let me go and erase my writing here. Where would the sun be on that star? You said right about the middle?
Yeah, yellow.
Yeah, yellow. It's done its yellow color. Now, did you have a question?
I was going about the writing, I couldn't see it.
Oh, that I just erased? Okay. Can someone call it out to him? Because I can't, once I erase it, I can't bring it back. The formula that we had gave us, okay, she got it. Okay. All right. So we're a yellowish kind of star. What else does that tell us? If you go to this table, then the yellow stars are between 5,000 and 6,000 K surface temperature. If you remember, we had in the text, we were about 5,800. Okay, so we're right in there on the upper end of this one. And then which type of star are we? G, exactly. Now that looks like it's on the lower end of this. Looks like F would be in the middle, but we're pretty close to F because we're really close to 6,000. So we're in the upper part of G, which moves us toward F there. Okay, that's the main thing to remember. We're an average star. Average temperature, average size, average everything. Okay, average lifetime. Okay, a very average star. Nothing spectacular at all. Okay, there is at the top of the second column of page 360, concepts applied, seeing a spectra, and it tells you what you can do and play around with, and it's kind of fun to do, only if you want to. Okay, so anyway, we're through with that. Now I'm going to go back in a little bit and remind you of what we've done, especially for folks who weren't here. We talked about the absolute magnitude of a star. Now that's not what we seem to think it is. That's the apparent magnitude. Our sun seems to be the very brightest star out there, but it's just because it's so close to us. Okay? So we don't really deal with apparent magnitude. We deal with absolute magnitude. Okay? And where our apparent magnitude of the sun, now why they put a really bright star as negative, I don't know. But they do. And the really dim ones are positive. So we look to be 26.7, that's apparent. Reality, absolute magnitude, we're right in the middle, 4.8. Okay? So don't sweat that too much, but just to give you an idea. Okay? So we talked about absolute magnitude. Brightness adjusted for a defined standard distance. We're an average star right in there. Okay. So we did that, apparent magnitude. Next thing we did, we just finished doing star temperatures. We even now have a formula you can use to calculate if you ever choose to do so. Okay? And then we have that. Now, why did I go back here? What do those two things have in common? Here's why we brought them up. This leads to the star types. Okay? Now this is a type according to color, type according to size, type according to anything. This is where the stars fall in their life cycle. Okay? And they call that the star type. This diagram, and how in the world they came up with this thing, two scientists, Hertzsprung and Russell. Russell, I'm pretty sure was American. Hertzsprung, I think, may have been German. I don't know if they say here. No, Denmark. Okay, Henry Russell in the U.S. and Egnar, or something like that, Hertzsprung from Denmark, independently developed this. Okay? What they did a plot of the absolute magnitude. And remember the sun was 4.8. That would be right about here, and sure enough, that's where the sun is. 4.8, that's the absolute magnitude, versus the stellar temperature, which you got from those calculations like we just did. And remember, our sun was right around 5,800. And sure enough, there we are. There's our sun right there. Okay? To plot this, and that gave you every star that you had the numbers for. And what happened, they saw they had these groupings. And they put in the colors, because the colors aren't there, but the groupings. Okay? And here are the characteristic grouping, or the star types. This eel-looking thing in the middle here is your, what they call main sequence stars. Main sequence stars. These are average old stars, middle of their life, just hanging around there being average stars. Some of these are very, very hot. Some of them are very, very cool. Some of them are very, 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 very bright. And some of them are very, 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 very dim. But they tend to follow this pattern. Okay? The hottest and brightest stars are over here, and the coolest and dimmest stars tend to be there. This is absolute magnitude. Yeah. Sun's right there, kind of in the middle. Huh?
I didn't see it.
Right there, sun, right there. You see what I'm talking about? Okay. That's right at 4.8, absolute magnitude, and temperature right around 5,800. Right there. There's bunches of stars that are hotter and brighter, bunches of stars that are cooler and dimmer. Okay, we're right in the middle. Okay. Now, there are another group they call the red giants. Now this just says giants, and it makes them blue. Why didn't they put red? I don't know. These are the giants over here. Okay? Don't sweat it too much, but here they call them red giants, which really adds a special feature to them. Red meaning they're on the cooler side, but they're still pretty bright stars. Apparent magnitude is very high up there. All the apparent magnitude stars in the main sequence that are this bright are much hotter. These are cool stars, meaning red. And let me get your name, please. Sorry?
Oh, hey, I'm sorry.
Shakaya? Okay, I thought that was you. But I don't just want to mark, don't want to mark the wrong person here and not mark you here. Okay, so there's your red giants in the blue. White out. Then this calls them the novas. What they're calling novas here are the supergiants. Okay? Now notice the characteristic of those. Those are very large apparent magnitude, absolute magnitude. These are the biggest of the stars. That's why they call them novas or supergiants. Okay? They can range from extremely hot to extremely cold. Okay? Supergiants. Now, there's another little grouping down here called the white dwarfs. And we'll get to those in a little bit. And hopefully this will make more sense. Now, this has no correlation there. Okay? These are the Cepheid, I don't even know how to pronounce it, Cepheid variable stars. Standard stars for distance calibration. And the guy named Hubble, Edwin Hubble, he came up with this, started using them, and everybody used them since. There's nothing on there that says anything about these. Okay? So I'll tell you just a little bit here. I'm basically going to read it from the book. By the way, for those who did come in a little later, let me go through what the sequence of things are. Not this sequence, other sequence. We're going to hopefully finish chapter 14 today, and we'll probably get started in chapter 15 today, up until 3:45. At 3:45, class ends, lab begins. 3:45, I've got the labs done up, we'll do the lab. Hopefully we'll finish it in the 2 hours. We'll see how that goes. Okay? That means on Thursday, we will continue the first 2 hours, not 2.5 hours, but 2 hours, in chapter 15. If at the end of those 2 hours we finish chapter 15, then the next 2 hours we'll have the lab in 15. But the last 30 minutes will be your test in chapter 14. So, now, not everybody is able to get a book yet. The bookstore obviously didn't order enough, so they're trying to get them in the next day or two, didn't you say? So if you want to wait until your book gets in before you take the test, you can, but you'll have to come during office hours and take the test. Okay, just to let you know where we are. All right, now let me read to you what it says about the Cepheid variable. This is on page 369 in the bigger book. Okay? Stars such as our sun and most of the stars you see emit a steady light because the force of gravitational contraction balanced by the outward flow of energy. That probably doesn't make a lot of sense now, but hopefully it will in just a few minutes. We're going to go a couple more slides. Variable stars, on the other hand, are stars that change in brightness over a period of time. They get brighter and dimmer, brighter and dimmer. Kind of like my screen does sometimes. I don't know if you notice it here, but on my computer, it's doing this not all the time, but a lot of times. Okay. Now, I'm sorry?
I want to ask you a question. You said the white
dwarfs.
Colder stars?
They range. The hotter stars are here, and the cooler stars are there. So they have a pretty big range, too. Not as big a range as the supergiants, and not as big a range as the main sequence, but they tend to be warmer than the red giants. Okay? So this indicates, here is the temperature range, this is the magnitude. Their magnitudes are small, that's why they're called dwarfs. They're all small, none of them are big. They're all small, and white indicates they're pretty hot, and that's why they're on this side of things, tend to be. The reds are cooler, they're huge, but they're cooler. So that's why these tend to be here, even some of the supergiants are there. And we'll talk about why in a minute. Yes?
We'll be teaching about is there a classification of stars called white or blue giants?
Say that one more time.
Are there any stars called white or blue giants that are just
white or blue giants?
Or they're just part of
No. Your giant stars, and we'll find out a little bit later why the giant stars are usually red. Okay? Yeah, but it's a great question. But we'll get there. Let me finish reading what I was doing about the Cepheid variable. I don't know if I'm pronouncing it right. Okay, a Cepheid variable is a slowly changing variable star. It gets brighter and dimmer, brighter and dimmer. It's used to measure distances. There is a general relationship between the period and the brightness, the longer time it takes for one pulse to go from bright to dim and bright again, the greater the overall energy output of the star. And it goes on from that. Once you get your book, you can read that to your heart's content. Don't sweat it. There's nothing that you're responsible for. It's just that they put it on here with absolutely no documentation or explanation of why it's there. It doesn't show up in the diagram. All right. Now that we know this classification, based on your temperature and your absolute magnitude, now we can talk about the life of the star, and hopefully all this stuff will kind of start making more sense. Okay? Now, those who weren't here before, you'll need to go back and listen to this, but we did talk about early beginnings of a star, and we got as far as the protostar stage. Okay, now let's go through what is happening. This is partly a review for the people who were here, a little bit of fill in the gap for people who weren't here. Out there in space, it's not just a vacuum. There's stuff actually out there. And there's some of these clouds, enormous clouds of usually hydrogen gas. Enormous, taking up huge, huge volume of space. Enormous clouds of usually hydrogen gas. Something happens, and this is where the mystery meat comes out. It could be some star exploded somewhere else, and a shock wave comes through, and it forces some of those gases into each other. When they're just gases, they're just floating around, not really paying attention to the next molecule of gas. If they do collide, they just bounce back off, and they just keep that. But when some shock wave or something like that happens that forces them together, and this is from the first half of the text, once they get close enough together, and enough of them get close enough together, they start clinging to each other because of gravity. Any two objects, when they get close enough together, they are attracted to each other. That's Newton's law of gravitation, universal law of gravitation. Supposedly he was sitting at his parents' farm, sitting under the apple tree, watched the apple fall and said, why did it fall? There must be this thing called gravity. He came up with a quantitative description of that gravity. That happens. They get pushed closer together, they get attracted to each other. All right, now what's happening then? They get attracted to each other and their mass increases because now they're a block. And then the bigger the mass, the more they attract more atoms, molecules, or whatever. So now they get bigger and bigger. Now as they get bigger and bigger, they get pressed closer and closer together. And I had you do this in the class last time. If you take your hands and press them together and rub, what do you notice happen? They heat up because of friction. You're absolutely right. So what we have is called gravitational collapse. The molecules, the atoms get closer and closer together, and they pull on each other, and they're always moving. They're never just hanging around. They're always moving. And since they're moving, they're combining, they're colliding with each other, and that's giving off heat, just like your hands. Okay? So that's what's called gravitational collapse. And as this happens, the density, that means the mass per unit volume, gets hugely increased. The temperature, because they're closer together, that goes up big time. The pressures, which is force per unit area, that gets bigger because they're now the same or increased force over a smaller and smaller area, so the pressure increases. Now, that temperature keeps increasing. When it reaches 10 million K, now that is hot, really, really hot. At this point, fusion occurs. Remember what fusion is? Fusion is the combining of two very light molecules, a nuclear reaction that forms a bigger molecule. And what you have at 10 million K is hydrogen fusing to helium. Hydrogen is the lightest element in the periodic table, the very lightest. And when two of them fuse together, you get helium, which is the next lightest, okay? And when that happens, everything explodes. I mean, that is one major explosion. Remember Hiroshima and Nagasaki? Tiny little explosions compared to nuclear fusion. Those were nuclear fission, splitting apart of big atoms. This is nuclear fusion, which is a lot more energetic, more power. That is what happens there. Now a situation arises. There is what they call a dynamical equilibrium, which is rather a strange combination of words. What equilibrium means is equal. It reaches some sort of balance. But what dynamical means, it's changing. Okay? So it's a changing balance. Well, here's what they mean by it. Gravitational collapse is making the star get smaller and smaller and smaller. Now, it's not a star yet. This is a protostar. Making it get smaller and smaller and smaller. But once you get fusion, that's blowing it up. So gravitational collapse is making it smaller. Nuclear fusion is trying to blow it up. That's where your dynamical equilibrium comes. The inward force of gravity is pulling it inward. The outward pressure of fusion is pushing outward. So it sort of reaches an equilibrium. Now, that doesn't mean it happens immediately. It probably takes an enormous period of time for this to happen. But once that does happen, that dynamical equilibrium, once that fusion occurs and it stops collapsing on itself and reaches this dynamical equilibrium, that's when the star enters the main sequence. Okay? Before that, it was just a mass of gases. Okay? When that mass of gases reaches 10 million K, hot enough for fusion to occur, now you're a protostar. When it reaches that dynamical equilibrium, it's now a star. A regular old average star. Okay? Main sequence. Some of these may be very hot, very bright, very dim, very cool. Anywhere in between, you're in the purple snake. Okay? Somewhere in that range of things. And all your main sequence stars are within that kind of band there. Okay. So that's the beginning of a star. That's the birth of a star. And by the way, I don't know if any of you listen to public radio. It's the station I usually have my radio on and coming and going. Occasionally I'll change, but most of the time I have it. On Friday afternoons, I think starting about 1 o'clock, they have a show called Science Friday. And it is really, most of the time, incredibly interesting. And Friday, when I was driving, I guess, home from work, I heard the last of one thing, and they had been talking about, goodness gracious, some biological science thing. And it was really fascinating. I don't remember what it was now. And then the next segment was on stellar. Goodness, they had a name I thought I was going to try to remember it. I've forgotten it now. It's basically a wave of energy whereby stars are born. Okay. Now this isn't Barbra Streisand. No, that's a different one. But this was how stars come into being, and it sounds really interesting. And I wanted to remember the term to say someone may want to write on that, and I've forgotten the term now. But anyway, you can look at that. I wouldn't say how a star was born. You're going to find Barbra Streisand there, but you might say stellar evolution. I don't know, something like that. That's what we're talking about here. But it's something new that our book knows nothing about because it's just come out in the last year or two. And it's incredible how much things are changing in astronomical fields. Because things we thought we knew, found out were totally wrong. So this is one of those new things. Okay. Now here is the illustration. And let me point this out. Your fusion only occurs in the core. We had a diagram earlier where the fusion only occurs in the core. That's the only place it's hot enough. That's the only place it's dense enough. That's the only place that, all the things happen for a fusion to happen. Now, this was what we call the radiation zone. Okay? In the radiation zone, things are expanding outward. Gravitational collapse is coming in. Radiation zone is pushing out, the effect of the fusion. And so that's what these are indicating. The outward force of the energy of fusion energy, the inward force of gravity. This part out here, remember in an earlier thing, we called this the convection zone. That's where the warm gases are rising and the cooler ones, when they hit the surface, they go in. So you get the combination of that, and that gives you the outline of the star. The stars are not solid. They are plasma, okay? They are, there's no surface there. What we see as a surface is the outer edge of those gases, okay? So that illustrates the dynamical equilibrium. The core is where the fusion happens. The radiation zone is where it's pushing outward. The gravitational collapse is pulling inward, okay? Mostly in the convection zone. And here's our stellar evolution, okay? Before it was a star, it was a mass of gases. We called it a gaseous nebula, okay? But then when it got hot enough to become a protostar, that's when there's no turning back. No turning back, it's going to become a star. So that's the phase where it becomes a star. Once it reaches that equilibrium, it enters the main sequence, okay? Now, where this is going is once it's in that main sequence, okay? The stellar evolution traces the path across the HR diagram, that's Hertzsprung-Russell diagram, okay? It's been in that main sequence for millions of years. That's for the hottest stars. Billions of years. That's for the average stars like our sun. Or trillions of years. That's those tiny little cool stars. It takes a long time for them to burn out. Okay? And we'll see that right down here. But once they do, once they burn out, here's what happens. Remember, it was a mass of gases. Most of those gases were hydrogen. Okay, the hydrogen fuses the helium. And guess what? Over time, it uses it all up. So that's what's happening. The hydrogen in the core, remember all that fusion is happening in the core, hydrogen in the core completely gets used up, fused into helium. Remember the fusion is what's pushing outward, so the core collapses. Okay. Hey, when it collapses, it heats up big time. I mean, it was 10 million K, which is really hot. Now it heats up even more. The outer shell, though, the core is collapsing. The outer shell is expanding and actually cooling even more. And when it cools more, that makes it red. You don't see the temperature of the core. You see the temperature of the surface. Okay? And that's why it becomes a red giant. Red because it cooled, giant because the outer shell expanded. Okay. Now, and that, remember, main sequence was here. Here was your red giants up here. Cooler, but bigger. Brighter. Okay. Now, brighter because, or absolute magnitude was greater because it's so big. Now, here's we're talking about the lifetime. What was O? Hot or cool or in between? What was our O stars? They are the hottest stars, exactly. Here they show them down here. The hots are over here. 40,000 Ks or hotter. And the coolest stars down here around 2,500 K. Those are the coolest. Okay? So, the O stars, the very hot ones, they only live for millions of years. Okay? They're short lives. The coolest stars, those M stars, they last for trillions of years. And where are we right in the middle? Billions of years. We think the sun's been there about 5 billion years, and we think it has about 5 billion years worth of fuel left in it. Okay? So they're in the billions, and that's us right in the middle. The mass determines the ultimate fate of the star. These small stars, they become one thing. The medium stars, they become something else. Those large stars, become something else, and the giant, big hot stars, they become something else. The mass determines the ultimate fate of the stars. So let's see what those fates are. Now, I don't find this a particularly impressive diagram here. But if you can imagine that purple snake, it was somewhere in here. Okay? So we're starting off in the main sequence. Okay? When this starts happening here, it becomes a red giant. So it moves up from main sequence into the red giants. Okay? Now, they don't really describe what the 1, 2, 3, 4, 5, they don't even number these are, but if it's a really, really large, massive star, not super large, but large, then it goes from red giant to supergiant. And that could go even as far over here. And I'll explain what's happening here then. When it's finally over, it drops down and becomes a white dwarf. If you remember, the white dwarfs are here, main sequence here, red giants here, and your supergiants here. The mass of the original star determines what the ultimate fate is. That's what we're going to get to next. Okay. Now, where we got to before, the star is approaching the end of its life. It's no longer has enough hydrogen, so the core collapses, the outer part expands and cools, so it becomes a red giant. Now, late in that red giant stage, remember the core was collapsing and heating up. There's no more fusion pushing out, so it's collapsing and heating up. What happens if it gets hot enough? In other words, if that was a massive enough star, then you get helium fusing to carbon. That has to be a way hotter thing to happen. So when that happens, now the radius decreases because that dynamical equilibrium happens. It doesn't seem like it should. It seems like it should get bigger. The luminosity also decreases because if it's a smaller star, it doesn't get seen as much. It moves back toward main sequence. And I can't see that on this, but that's what they're describing. It could go from main sequence to red giant, and if it has enough helium and gets hot enough, fuses back to carbon, then it goes back into main sequence. Now it's fusing helium to carbon, not fusing hydrogen to helium. It's back to main sequence stars. All right. And that happens to most stars, even the coolest, the smallest, all that usually goes that route. So let's start with the least massive stars. Now you finally use up all the helium, fusing that into carbon. Now the helium's gone, the carbon's gone, fusion is exhausted. It's not big enough to do anything else. The instabilities blow off the outer masses of gases, okay? And that forms that planetary nebula. Remember that? This is going to be a real quick slideshow here, going in reverse. There it is. Okay, that's your planetary nebula. This happens after all the helium, all the hydrogen is fused to helium, then helium fused to carbon, and now it collapses in the middle, right there, and the outer shells blow up. And that's called the planetary nebula. Guess what? These are gases that get thrown back into the universe. Okay? And some of these then later will get bound back together and combined with other masses of gases and form new stars. It keeps happening. The cycle goes on. Okay? That's what the planetary nebula is. Has nothing to do with planets except it's gases floating around a central area. That's what we mean by planets. And nebula means it's going back to a mass of gases. Okay. So. All right. Nope. Yeah. This one. Okay. Now, the helium is used up. Hydrogen and helium fusion is exhausted. instabilities blow off the outer layers of gases and make a planetary nebula. What's left? Carbon was the last thing in that core. Okay? It's contracting and heating up. Heating so hot, it becomes white. Remember these gases up here, they're red. They're pretty cool. But that's because they're way out there. Your white dwarf is really compact. Now, what happens to carbon if you put it under incredibly high temperatures at incredibly high pressures? Does anyone know? It makes a diamond. Okay? Now, we don't know this for a fact, but this is some, we had a guy here many years ago, decades ago. He was very helpful. He had been, okay, y'all know what I mean by the Soviet Union? Okay? That was, after World War II, that was, Russia gathered all these other countries around it and made it the Union of Soviet Socialist Republics, USSR. Or a song or two about that, right? Okay, now, he was, and USSR was what we were in the space race with. The USSR stole as many of the German scientists as they could, and the US and the Western countries, they stole as many as they could. They persecuted everybody else, but those scientists they wanted to keep and make their space programs, and they did. So we were forming NASA, they were forming their space agency, and we were in the space race, and they started off winning, pretty big time, but we ultimately got to the moon first, and then the Soviet Union kind of broke apart, so it no longer exists. You have Russia still, but you don't have the other. Well, this is Dr. Bolshinsky. Dr. Bolshinsky was a Russian, but what Russia did when they formed the Soviet Union, they wanted to keep Russia as the major influencer. So they would ship out Russians to all the other Soviet republics so they would keep up big influence there. So he was sent to the Ukraine, okay? But they were all part of the USSR, so that was fine. And the USSR had the space agency. That was fine. And he worked for the USSR space agency. But then the USSR, it kind of blew apart, okay? It failed, okay? And they split up into republics again. But once those Russians had been in the other countries, they wouldn't let them come back to Russia. So he was stuck in Ukraine. Ukraine wasn't rich enough or powerful enough to have its own space agency. But he worked for the USSR space agency. That now became the Russian space agency, but he couldn't work for them anymore because he lived in Ukraine. So he immigrated to the U.S., and he was really a neat guy. He had a lot of talents, ability, very, very bright. And he told me this story. The very first white dwarf they discovered, the astronomer, this just shows how strange physicists and astronomers are. They named it. Does anyone have a clue of what they named that first white dwarf they found? Lucy. Why wouldn't you name a white dwarf Lucy? Isn't that the first thing that came to your mind? No, not either. Here's why. It was made by carbon fusing under enormous temperatures and not fusing, but being pushed together in enormous temperatures and pressures. What did that become?
Diamonds.
And does anyone remember a Beatles song? Lucy in the sky with diamonds. That's why they named the first white dwarf Lucy, because of that song. You know, these are Russians, but they still followed the Beatles. Okay, so that's what makes a white dwarf. It is white because it is incredibly hot. But it's not hot because of fusion, it's hot because of gravitational collapse. That's why it's a dwarf. Very bright, very hot, but very small, not very visible. That's why the white dwarfs are way down here in the Hertzsprung Russell diagram. They're not very much magnitude, absolute magnitude, but they can have a whole range of temperatures, tending to be on the hot side too. Okay. So that's what happens to the least massive stars. Okay, didn't get quite far enough. The carbon core contracts to a white dwarf. Then, because there's no fusion to keep it hot, it slowly cools to a black lump of carbon. Now, why do they say black? Do we know it's black? No, we mean it's not emitting light anymore. So you can't see it. That's why they say it's black. You see the star because it's hot enough to produce light. Once it cools, it doesn't produce light anymore. Now, a little bit later, in the end of the chapter, we'll talk about dark matter. Some of that dark matter has to be these black lumps of carbon, which could be coal or it could be diamond. Guess what? Those are the same chemicals. Coal, soot, that black, messy stuff, same chemical composition as a diamond, which is hardest material known to man. Okay. Now, and there's a picture, maybe a better picture without the color, though, of your planetary nebula, and guess what's in the middle there? Your white dwarf. Okay. So that's what another picture of a planetary nebula. That's when instability blows off the outer layers into a planetary nebula. Carbon core remains, contracts to a white dwarf. White because it's so incredibly hot, dwarf because it's so incredibly small. Okay, but it then has no more fusion, so it cools slowly, and then you don't see it anymore. Okay. Now, let's go to more massive stars. Okay, that was the small massive stars. Kind of like our sun, okay? Get a little bit bigger. The more gravitational contraction and heating, now the critical temperature goes from a few million K to several million K to 600 million K. Now that's hot enough for carbon to start fusing. And carbon starts fusing heavier and heavier nuclei. And here, by the way, there was hydrogen fuses to helium, helium fuses to carbon, carbon ultimately fuses to iron. Okay? You just keep getting bigger and bigger atoms. Okay? So the heavier nuclei fuse up to iron. Once it gets to iron, they kind of stop. Okay? Kind of. All the fusion energy sources are used up. You aren't going to fuse any greater than iron. Sort of. Okay? The energy expansion pressure is lost because no more fusion. The dynamical equilibrium is disrupted. Now, before, you just formed a planetary nebula. Here, you form something even bigger. These are called nova. The star actually collapses and then rebounds. It's sort of like taking, y'all remember the little balls they call super balls that really bounce like crazy? It's taking one of those and throwing it as hard as you can against the wall, and it comes back. It feels like it comes back even harder. It's not, but it comes back really hard. This is what happens. It collapses on itself with such force and then rebounds. That's what's called the supernova. When that happens, that rebound, now that forces, because this is naturally occurring fusion, goes only up to iron, now you can fuse material beyond iron. And if you notice here, our periodic table goes way past iron, so all these elements down here are fused when these supernovae happen. Now, there's not a lot of them, but there are some. Those are rarer materials. And elements beyond iron are created by that explosion, and then they're distributed throughout the universe. And that's why we have gold, silver, platinum, uranium, plutonium, all those heavier things come because anything beyond iron gets created in those supernovae.
So it falls back to Earth, you were saying. That's really
Say again?
It falls back to Earth?
No. We're way dust out there, yeah.
Okay.
These just are distributed throughout the universe. But you see, we were formed as a remnants of our sun going through whatever it went through, okay, when it was being formed. some of the materials got sent out and grouped together. We'll talk about that in the next chapter. Now, the subsequent events depend on, again, on the mass of the remaining core. You still have a core, okay? It's not going to fuse anymore, but you still have the core. So the next slide takes us to the two stages of your more massive stars. Now, up till now, we've been getting from small to bigger to bigger. This next slide, we're going to go biggest and then smaller. I don't know why they did that. It's sort of backwards, it seemed like, but we'll do that. Actually, the slide goes in the right order, but the diagram goes in the wrong order. Okay. So I'll let y'all catch up because there's a lot of writing on this and a lot of blah, blah, blah. Now, what we're talking about here are the remaining core. This isn't the whole star. Most of the star is blown up and sent out in the universe. Okay? This is what's left over in the core of that star, which is a very, small amount of the star, but probably pretty dense. So you're talking about a lot of stuff here. Okay? I'm saying that because we're going to be comparing some things. So we'll look at that in a bit.
But this stuff is on the slide that you have.
Yeah, all these slides are out there in Blackboard, but then they'll also be in the YouTube videos because that's exactly what I'm recording now. And you'll hear us talk about them too. Furious writing going on. Okay. Okay. I thought you wanted my picture. No, I'm just kidding. Okay. Okay, everybody caught it? Can I move to the next slide? Anyone? Oh, no, still writing. Got it? Okay. All right, so here's the end states for the biggest, the most massive of the stars. Okay? Now, what if that remaining core is between 1.4 and 3 solar masses? Now, wait a minute. Okay. That doesn't seem very big until you remember this is the core. Most of it's blown into space. The core is still about 1.5 to 3 solar masses. Okay? If that occurs, then the gravitational pressure fuses and fuses, pulling things together. No explosion to push out. It fuses, so now protons and electrons are fused into becoming neutrons. Remember, protons have a positive charge, electrons have a negative charge, protons have a big mass, electrons almost no mass, but the neutrons are about the same size as protons, just a slight bit more, the reason they're fused protons and electrons together. So, you now have neutron stars. Now, this is a rather bizarre issue here. Anytime you have a neutron star, and of course it's rotating, and when it's rotating, it's magnetized. Now, if you take Physical Science 2, which is the first half of the book, you'll realize that magnetization occurs when you have moving charge. Okay? Well, the movement comes from the rotation, but where's the charges? They've all been fused together. They haven't all been fused together, but most of them have. But the remaining charge now creates very strong magnetic fields. Okay? So what we have is a rotating star, but it's also oscillating. So sometimes the magnetization is pointing toward you, sometimes away from you, sometimes. So that star looks like it pulses. Now this isn't quite the same as the C-fed variable stars, but it could be in the same class. Those are called pulsars, rotating magnetized neutron star. Okay? It's rotating and also somewhat oscillating, giving you this variable magnetization, which gives you the pulses. Okay? Now, that's your massive stars, but not the most massive stars. What happens to the very most massive stars? What if your remaining core was not between 1.4 and 3 solar masses, but something even greater than 3 solar masses? Now remember, this is just the core we're talking about. What happens now is your gravitational collapse overwhelms all known forces. Okay, in other words, we don't have the physics to tell you what's going on there. That gravitational collapse, not just enough to make a neutron, protons and electrons in the neutron, more than that, collapses completely. Absolutely nothing. It's just a complete collapse. The gravitational effect here is so great that light cannot escape. You can't have magnetization. Nothing escapes. It just sucks in and sucks in and sucks in. This is called the black hole. Hole because you see matter falling into it. Black because you can't see any light coming out of it, because it doesn't allow any to escape. Now, these are incredibly, incredibly massive things. Later, in this chapter, we're going to talk about galaxies. At the center of every galaxy is a black hole, an enormous black hole from some enormous star that collapsed. Okay? So that's your last, the most massive breakdown. Now, remember, black is not a color. Black is the absence of light. Okay? So that's why we call them black holes. Light's not coming out of them. How do we even know they exist? Well, a few things. We can sense their gravity acting on things around them, but we can't tell anything's there. But the other thing is, when something else passes behind it, it disappears, okay? Because no light gets through it. But then when it comes on over here, you see it again. So we know there's something there that's blocking all the light from coming. Okay, that's a real layman's definition of it. Okay, everybody got this? Yeah or no? Oh, still writing? Okay. Now, by the way, if you're following in the book, we went past page 361, 362, 363, and here are some of these diagrams that, to me, they look like they go really well, and then they do some weird things with the diagrams. But they're nice diagrams. Okay. But I don't want to leave it. Now, I'll tell you this too. My PowerPoint slides came from an earlier edition. The newest edition of the book, they never sent the PowerPoint slides, so some of the things on the slideshow won't quite look like the same ones in the book. The books are a little bit nicer. They were a little more recent. They use better technology putting them together.
So the test really consists of knowing these different the definitions, or
some of it will be definitions. Now, most of your test is going to be multiple choice. So it'll either, for instance, if it is a word, you'll have 4 choices what best describes it. Or it will be a process, which is part of this process. You know, it'll be something like that. So if you know the general picture of things, you got it knocked. Now let me also say this. I can't remember if I said it before or not, but I'm glad you asked the question. For every test you take in this class, you can bring to the test a formula and equation sheet. Anything you want to bring right on a regular piece of paper, front and back, you can bring to every test. So I'll say this later when we get to the end of the chapter. I'll give you some indications of where I think you can get stuff. But this is, I don't think math or science, either one, are memorization. I think it's putting together concepts. So look up the facts, write the facts down, put them together. That's mostly what your tests are going to be. So work up a formula and equation sheet for every test you take. Okay? You can use the book for that. You can use your notes. You can use the PowerPoints, whatever you want to write down.
So
you can. Yeah. What were you going to say?
Some are going to be, you're going to have some things you're going to have a definition of. When it's multiple, you're going to be formulas. Are you saying that?
No, we're not going to have too many formulas in this course. The ones that we have are made up of things they sort of kludge together from earlier part of the book. Since you haven't had the earlier part of the book, I don't think it's fair to test you on that. So it's mostly going to be concepts and like definitions, progressions, you know, cause effect, that kind of stuff. Multiple choice type questions. Now every now and then there may be a fill in the blank, and there could be, I'm trying to think if there are a few simple calculations. I know in the, Physical Science 2, physics and chemistry, you can't do without some calculations. So there will be some calculations there. And this one, not as much. Okay. All right, to move on? Second? No? Okay. While we're waiting, on the top of page 363 or wherever that is in figure 14.12, it shows the blown out layers of stars can form beautiful ring-like structures seen here. This one's called the Cat's Eye Nebula. It's a mass of gases and kind of looks like a cat eye, like a marble. Through? Okay. All right, so here's the stellar evolution, the diagram for it. Not quite the pretty one that's in the text now, but if you got a text, you'll see this on page 363. But it says the same thing. You start with a mass of gases. That's called your gaseous nebula. That's your nebula. Mass of gases. Enormous mass of gases. Something happens to make it start collapsing. Some shock wave or something happens. And as it's collapsing, it becomes a protostar. Now, what the protostar is something that the mass of gases starts heating up, heating up. When it passes the heat that it takes for hydrogen to fuse the new helium, that's when it becomes a protostar. There's no turning back now. Before that, this mass of gases could do, but if it didn't get hot enough, it could spread out again. Once it starts fusing, that becomes a protostar. Not a star yet, but at this point, it's going to become a star. Not every nebula is going to become a star, but every protostar will. Okay, and when that dynamical equilibrium is finally established, it becomes a main sequence star, the purple snake. Okay. Now, let's start with the low mass. It lives in its main sequence for billions or trillions of years. Okay? But then when all the hydrogen is fused in the helium and it collapses, the core collapses, and the outer parts expand, it becomes a red giant. Okay. Now, if then the core in continuous collapse gets hot enough for helium fusion to go to carbon, then it will continue down and actually send out, and this is called a planetary nebula, blow off the outer parts, the inner part has become carbon, and that becomes your white dwarf. Hot, 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 but not fusing anymore. And then as that hot carbon cools, it becomes a cold lump of carbon. And that's probably what some, if not most, but some of the dark matter is. And we'll talk about dark matter later. So let's then go to the mid-mass, okay? In the mid-mass stars, the red giants are bigger because they have more mass. Then they go to the planetary nebula, and when they collapse, forming carbon, again, helium fusing in carbon, then it becomes a white dwarf and goes back to cold time. These are usually hotter and bigger and longer lasting white dwarfs, but they still are just white dwarfs. Those are the ones down here. The cooler ones were probably from the low mass, the hotter ones from the high mid mass. All right, now here's where the diagram, I think, sort of falls. I don't know why they do it this way, but they do. The very highest mass of the stars, they form enormous red giants. And those enormous red giants, when they collapse, it's not just a planetary nebula, because these go past the point of carbon, of helium fusing to carbon. These go to the next step for carbon fusing up to hydrogen. Up to nitrogen. Up to iron. I don't know where my brain is. Up to iron. And when finally that happens, and then they collapse and get so hot and they blow up, that becomes a supernova. Now, the smaller of the supernovas, which are huge, by the way, and those are the ones up top, the massive super red giants, okay? The less massive of these become your neutron stars. The more massive of them become the black holes. So why in the world didn't they reverse these two? I don't know. I would have put this one here and this one up here, because this is the most massive. Okay. Now, this doesn't mean it's smaller than that. These could be huge. It just means it's a black hole, not just a cold lump of carbon. Okay. Any questions? Y'all are keeping up with time, right? Okay. All right. Yes. Need to go back? Oh. Okay, I can't hear it. Okay, say this again.
Do you control the thermostat?
No, I don't. They changed it. In the old days, they had one you could adjust. They put in these new ones that are all controlled by somewhere else. And I have absolutely no control of them, heating or cooling. You feel like it's a little cool? I was feeling a little cool too, but I'm right under here, but near the windows, I bet you it's cool too. Now, some people have short sleeve shirts and shorts on. I don't know how you're handling it, but that's okay. All right. Now, your picture in your text, you'll find is a lot prettier picture than this, but it has the same results. Okay? And they even put the neutron star above the black hole. I don't know why they do that. Okay. Now, let's look at structures bigger than stars. Whoa, can you get bigger than stars? Of course you can. Now, this you may find hard to believe. We've said our sun is average in just about every way. There's one way it's not average. Most of the stars out there are at least binary. Two stars gravitationally bound to each other, and most of them out there are binary stars, or bigger. Very rarely will you find one that's isolated, like our sun. So we're not average in every way. But then get this, okay? If you had two stars out there bound together and then had planets around them, there would be sometimes the planet would be exposed to two stars, some to one. How in the world could you support life with that kind of variation in temperatures and pressures? And I don't even know. So if we didn't have a unitary star, a single star by itself, I don't think we would exist. I don't see how life could be. Now, I'm not an expert at it, but that's not my impression. So ours is not normal in that way. Now, beyond binary systems, you have star clusters. Now, these star clusters are tens to hundreds of thousands. Now, this is not really clear. Does this mean tens of thousands to hundreds of thousands, or 10 stars to hundreds of thousands of stars? I don't know which one it means, but even larger, gravitationally bound stars. Now, these are not like the binary stars, which are relatively close to each other. These are just groups of them that tend to hang around each other and stay around each other. Not close enough to really affect the planets, okay? Now, often these star clusters share some sort of common origin. Maybe there was an enormous mass of gases, and when it started its collapses, it made several stars at once, okay? So that's what it means, share a common origin. All right, now bigger than star clusters, we get up to galaxies. Now, if you may think, maybe you, like most people in the past, have thought, we're the center of the universe. Our little planet is the most important thing out there. No, we're a speck of dust in the universe. We are negligible in the universe. So you might say, well, the basic unit of the universe is a star. No, it's not. The basic unit of the universe is a galaxy, which are billions and billions of gravitationally bound stars. Now, what does that mean? There has to be black holes involved, because they can't be gravitationally bound by anything else than a huge, strong black hole. Okay? That's the basic unit of the universe, galaxies. Now, there are larger scales still than galaxies. Just as we have star clusters, you can have galactic clusters, clusters of galaxies. Okay? And you can have superclusters of galaxies. Okay? And guess what? There are billions and billions of galaxies out there. And every one of those galaxies has billions and billions of gravitationally bound stars. And those gravitationally bound stars are probably half of them bigger and stronger and more powerful than our star, and half of them are weaker and all that kind of stuff. And yet we're a little speck of dust circling on a very average star. Okay? The scale is unbelievable. Unbelievable. And by the way, now we've moved on the page 364, there's a closer look, observing with new technology, and basically this is telling you the different ways, different kinds of telescopes we can focus on the stars and give them all kinds of new information. We think of a telescope as being light telescope. You look and see what you see. But they can look with telescopes that read X-rays, okay? Very high energy rays. They can have telescopes that read infrared, very low energy, and get completely new information. They can look at telescopes that do gamma rays, which are way more powerful than X-rays, okay? And then there's some they call very large array. There's just a whole different kinds of telescopes. Now, remember when I talked about neutron stars? In your text, this is before this, but there is an illustration of a neutron star and how the rotation axis may be here, but the radiation axis or magnetic axis is here. So when it's rotating around, that is what gives you the pulsing. When it's facing you, it's strong. When it's away from you, it's weak. So it's pretty incredible how that works. Okay. Now, early in the chapter, last time when we looked, I talked about light pollution. Finally, here on page 365, they talk about light pollution and have a few questions. That may lead you into a paper topic or so. And they show an illustration here, a jet of particles streaming out of the center of a galaxy at nearly the speed of light, which is incredible because particles aren't supposed to even get close to that. The jet is powered by some monstrous black hole estimated to have swallowed up matter equal to 2 billion times our sun's mass. That's a lot of mass. Okay. All that preceded the galaxies. Now, there's a good picture at the bottom of 365 of a little bit of our galaxy, the Milky Way galaxy, that part that we can see from Earth. Okay. Everybody finished with this slide now? No? Okay. On page 366, there's a closer look, a big closer look, on extraterrestrials. Anyone remember E.T.? Okay. Big movie back in its day. The likelihood of something like that, not very likely. Because think of this. Remember, he was trying to communicate to his home star, which was so far away. Hey, one of the stars, I'm just going to read a little piece of this. One of the stars that they think maybe somewhat have planets sort of like Earth is about 53 light years away. Okay? That's one of the closer ones. That means if we were to send a message to it, it's going to be 53 years before it gets to it. That means going at the speed of light. And then to get an answer back is another 53 years. You can't fit that in a 2-hour movie. Okay? Just not going to happen. Okay? That little boy would have been his grandson by then. Yeah, I mean, no, it's just not happening. Okay? But it's a really good blurb to read. Okay? All right, to move on or not? Okay. So let's look at our galaxy. Now, it was given its name because what we first saw of it, we didn't know that's what we were seeing, but in a very, very dark night, not anywhere near a big city like Birmingham or even Bessemer or anything else, way out in the boonies, okay? You look out at the sky, and sometime on a cloudless night, you'll see what looks like a diffuse band in the dark night, okay? Now, that's not a band playing music, no, that's just a band of light there. What you're seeing is billions of stars, some bound in what we call galactic clusters. That's part of our galaxy, just a little part of it. Now, what's the structure of our galaxy? At the center, it's sort of like a solar system, only on a much bigger scale. At the center, they call a galactic nucleus, okay? A galactic nucleus. Lots and lots of stars. When I say close to each other, relatively close to each other. They're still way, way, way far apart, but they look like they're close. And then around that nucleus is a rotating galactic disk with curved arms on it. And that diameter of that disk is 100,000 light years. So in other words, if you were to flash a flashlight or a strobe or something at one edge of the galaxy, it takes 100,000 years for it to reach the other side. Okay, that's at the speed of light. Now, consider this. Look out there and see a star. Not a planet, but a star. Okay, you can't see it now, but at night. If you were, you don't know if that star is still there. It may be that star is so far away, it's already blown up. But you're still seeing the light from a few hundred years ago. It may have blown up since then. So it's unbelievable the distances. Okay? Around this galactic nucleus with the rotating disk, there is also a galactic halo. This is sort of a spherical type shape of other globular clusters of stars. Okay? About 150, they say. I don't know where they get that, globular clusters. That's in the outer reaches of that. So here is an artist's rendition of this. Okay, first, here is a telescopic picture on a very cloudless night of that Milky Way. This is a diffuse band of stars here. It looks like it's light, but it's not single light. There's just so many stars so close, not close together, but lined up with each other that you can't distinguish one from another. Okay? Now, we're in that band, and we're seeing the edge of the band. These are here could be in these spherical galactic halos, okay? Or it could be we're looking at some of the ones that are just a little bit further from the band. It's hard to say, okay? But that's what the Milky Way looks like, and how they got its name. It looked like someone spilt milk across the sky, and they called it the Milky Way. Okay? You still writing? Okay.
So that's the Earth fit in all this Milky Way.
What's this again?
Where does the Earth fit in at? Where does the Earth fit in?
Okay, excellent question. I think in the next slide or two we're going to find this. Okay, we're not in the galactic nucleus. We're in one of these rotating arms of the disk. Okay, we're kind of out there. Guess what? Just about midway out. Okay, we're so average in everything. Okay, we're actually a little bit further than midway out. Okay, can I proceed after the picture taken? Okay? All right. Were you through? You want it back one? Okay. It's the same words here. So, here's what it looks like from above. There's your galactic nucleus, and it's not a perfect circle like that. It's a glob. Okay, then you have these spiral bands coming out of it. Here's where we are. We're about 2/3 of the way out, maybe 3/4 of the way out. We're near the edge of it. We don't ever even see this. All we see with the Milky Way is back this way or back this way. We only see a little bit, okay? And it's pretty amazing. Now, if you were to come to the edge and look at this, there's your galactic nucleus, and it takes up a lot of room. But these stars really aren't that close together, but you just got a lot of them in relatively close proximity. Then these arms here look like this disc. Looks like a disc here. Now, this is your halo. It is above and below this on the sides here, and these have these globular clusters, other small clusters of stars. Okay? But we are in the band, like I said, about 2/3 or 3/4 of the way out the band, one of the bands. And basically all we are seeing is a little bit this way, a little bit that way, and maybe a little bit above and below. You know, it's, we're kind of immaterial. Okay. Now, I don't know what it would be like if you were in here. You would think the stars would be so close that the whole night sky would be very, very bright. Not super bright, not like daylight, but, you know, it would be a much brighter sky. Okay. Okay. Light pollution would not be as big an issue. Okay. Still writing. This is the same verbiage that was on the previous slide, so there's no new writing here. It's just a drawing. And later, yes?
What time did you tell me you don't have something to wear?
What time, what?
What time for my
3:45. What time is it now?
3:25.
3:25. Okay, we're not going to get very far in chapter 15 then. So that probably means that we won't have a lab next time either, because I don't think we'll finish the chapter. Okay? All right, to move on? Okay. On page 367, there is a blurb at the top on Jocelyn Susan Bell Burnell. Boy, she has enough names, doesn't she? Now, I don't know if she's still alive, but she was born in 1943. And she was born in Belfast, Ireland, which is actually in the UK, but on the island of Ireland. When she was working on her PhD, she was under the supervision of a guy, University of Cambridge, and she worked at one of the labs, the telescopes there that they use at the college, Royal Observatory. But When she was there, she discovered the first pulsar. She may have even named the first pulsar. I don't know. But even though this is the first time it was ever discovered, first time identified, she did a fantastic job of documenting it, showing it, all like this. The Nobel Prize went to her boss, not to her. The excuse they gave was she wasn't a PhD yet. She was still working on it. And they only gave that. In reality, it's probably partly because she was a woman, okay? You would think that wouldn't happen in this modern of time. But this was a few years back. It did. And her boss was so incredibly angry at that. He complained to the Nobel Prize Committee they would not hear any of it. Okay? They probably shared some of the prize with her, but officially it went to him, not to her. Just a little tidbit. Okay. There are other galaxies out there, like we said, billions upon billions of them. We only know of a few that are closest to us. Our nearest neighbors is called the local group. These are some dwarf galaxies, really, really small, only about 1,000 light years in diameter, whereas, remember, Milky Way is about 100,000 light years in diameter. So they're much smaller than we are. The nearest dwarf galaxy is being disrupted by our gravitational activity, and probably at some point is going to be drugged into the Milky Way. Just our bands will get a little longer. Okay. The next closest major galaxy is 2 million light years away. That's 2,000 times the size of our galaxy. Our galaxy is 100,000. Multiply that by 20, and you get how far it is to Andromeda. Very similar to the Milky Way. The Hubble Space Telescope is taking some fantastic pictures of it. It was named Andromeda because one of the ancient Greek constellations was named Andromeda. And we found out one of the stars in that thing was not a star at all. It was a galaxy. It was so incredibly far away it looked like a single image. Now we know it's not. Okay. Let me see. Here's a picture, I think, of Andromeda. There's the galactic nucleus, and here are the spiral bands. Looking this way, that would be your, what do they call it in the last slide? Disk, rotating galactic disk. Okay? And then around here would be your globular, your halo. You can't see the halo very well here. It's so stinking far away. Now, what's this very bright thing back there? Maybe another galaxy, even further away. Maybe that one too. Or this could be a star that's closer to us. It's hard to say. Now, how do you classify galaxies? Well, good old Edwin Hubble, you'll see his name a lot. He came up with this classification scheme. Elliptical galaxies. Now, this would almost be elliptical, except you can see bands in it. So that makes it a spiral galaxy. So the Milky Way is, Andromeda is. Elliptical galaxy, you don't see the arms in it. It just looks like an ellipse. A barred galaxy that has spikes coming out of it. And then irregular would just be a massive collection of stars. Okay? We are in a spiral galaxy, and Andromeda is also one. Okay? All right. Still picture taking. Okay? All right to move? All right, let's look at the life of a galaxy. Okay? Now, all this is based on a theory. Now, this is not a television show. There is a television show by that name. That's not what we're talking about here. The television show was based on the Big Bang Theory. Okay? Now, we don't know that this is true. In fact, it probably isn't totally true. but it's our best guess of what happened. They've had many other guesses over time. All of them have fallacies. This one probably does too. We just haven't discovered what they are yet. Now they think the entire universe evolved from an explosive beginning. That's way beyond anything I can imagine. The entire universe coming from one explosion. Okay. Now, here are some of the supporting evidence. We are able to track back microwave background radiation that seems to go back and point toward a single source for everything that we see and know and understand. And beyond that, there's still large-scale expansion going on. Okay, so that also indicates it came from some explosive beginning. The relative abundances of the elements. Now remember, just from stellar formation, you don't get much bigger, not much more than iron. But there's lots of things bigger than iron. Now those supernovas, yeah, they'll create some of this stuff, but not in the abundances we see. So evidently there was something way back then that created as much of the basic elements as we see. Now, I can't tell you much about this, but the diffuse cosmic background radiation, for instance, being collected by the Kobe spacecraft, that's more of this kind of stuff that they're collecting. It seems like it's coming from a single source. Now, as I said, the universe is still expanding. And this question here, I think, okay, is it going to expand forever, or is it going to finally stop expanding and then collapse on itself? Okay, now, of course, this takes quadrillions of years to do any of this, so we don't know. We've only been observing an incredibly small amount of time, so we don't know. But here's something that Edwin Hubble discovered that kind of, to me, puts the kibosh on this. Not only is the universe expanding, it's accelerating and it's expanding. Things are moving apart at an acceleration. Now, what forms an acceleration? From the first half of the book, a net force. So that means there's some force somewhere that's making us spread further and further apart at higher and higher rates of speed. Nobody understands.
No one knows that, though.
What's that?
No one knows that.
No one knows that for sure. Except they do know we're accelerating. We don't know what could be causing that.
So you're saying that the universe is accelerating.
The universe is expanding at an accelerating rate. It's just unbelievable.
What does it have to do if the universe is expanding so much? What is it doing to the Earth?
Well, we're just hanging around our sun. We don't notice anything.
We're still stuck in this particular galaxy.
See what?
We're stuck in this particular galaxy.
Oh, yeah, we're stuck in this particular solar system. In this particular galaxy, in a bigger cluster of
Everybody
galaxies.
else is gone.
Huh?
And everybody else is gone by
Everybody, we are moving further apart, okay? We are, and in a later chapter, we're going to talk about the speeds at which we're doing things. It's unbelievable. But we don't notice because we're just here. You don't feel like you're spinning, do you? The Earth is spinning. That's why the sun rises and the sun sets. We're spinning. We don't notice the spin because it's so big. Now, here is the example they give. Any of you ever baked raisin bread?
Yes, I have.
Okay. When you do, it starts off, the raisins are pretty close together, but as the loaf expands, what's the word rises, then the raisins get further and further apart. Okay? But they keep at a relative distance. For instance, A to B here, these two raisins, 1 centimeter, and A to C was 5 centimeters, and A to D was 16 centimeters. Well, sometime later, after it's expanded, A to B is 2, A to C is doubled to also 5, and A to D is doubled to 32. So this went much further. This only increased by 1 centimeter. This increased by 16 centimeters. But we're expanding, but we're expanding at an increasing rate. So that's a pretty good thing to consider, but it doesn't answer all your questions. Okay, I'm not sure anything will. All right, to move on. There's no new verbiage here. It's just a new picture. Okay? All right. Now, this is the illustration of what we think may have been happening with Big Bang. Somewhere back here it all began. And now, galaxies were thrown out that way, this way, all sorts of ways. We're just going to look at these over here. These were thrown out this way and get further and further apart, but they're also getting further and further apart from each other. How long will this continue? We don't know. It seems to be accelerating. We don't know why. We can't imagine what force could be causing that to happen. Okay. That was the last slide. But say again? Yeah. Now, let me back off just a little bit. Anyone remember the old television show Star Trek, and then they came out with a few movies? Okay. One of my favorites of all time. This television show anyway. That myth that spaceships could have instant two-way communication, it cannot happen. Now remember, that was supposedly interstellar travel from wherever the Federation was, and they're galaxies away, right? If they were just in our solar system, and Kirk said to Huru, or whatever her name was, send thing to the Federation headquarters. If they were on Mars from Earth, it would take 4.3 minutes for that transmission to go from us to Mars, and another 4.3 minutes to come back. Us to Jupiter would take 35 minutes to go one way and another 30. That would be an hour and 10 minutes. Show's over with, before you got an answer. Okay. Of course, they could compact things. But how about Saturn? That would take 1.2 hours to get from us. Now, this is in one solar system, not galaxy, solar system, okay? 1.2 hours, okay? Now, have you been here before today? Huh? Okay, yeah, okay. I couldn't tell from that. Uranus, 2.6 hours, one-way communication. 5.2 hours return call. Neptune, 4 hours, one-way, 4 hours back, okay? So you sent the message at 8 o'clock this morning. We'd have gotten it, they'd have gotten it at 12. We would have been getting a response now, 8 hours later. Pluto, 5.3 hours. Okay, so let's stay in our galaxy. How long would it take for us to send a message from one edge to the other edge? 100,000 years, okay? So how in the world was Uru going to contact Federation headquarters? Not in their lifetime, not in anybody's lifetime. To Andromeda Galaxy, 2 million years. That's the closest galaxy. Hey, not going to happen. Okay. Now, the blurb at the top of page 369 to me is an incredibly interesting but complex thing, dark energy. Energy we know is out there, but we can't detect the source. It's pretty incredible. Now, there's also an example there with some calculations. I'll let you look at that. Equation 14.3, they just throw out there. It's Hubble's law, and you can look at that and follow along if you'd like. Okay, there's 14.6 and 14.7. But then on page 371, an entire page on dark matter. And that's even more fascinating to me, or at least as fascinating as dark energy. You know it's there because you can sense some gravitational effect from it, but that's all you can do. And then they have a few models here that they have for the expanding universe, and they're interesting to look at, but I don't really see too much there. Okay. The end of the chapter. Second. Okay, I'll try not. I'll say this every chapter, so get used to it. Nothing replaces reading the text. Nothing does. I hope you read it before I even start talking about it. I'll just give you this illustration. Back when I was in college, and I went straight from a small rural high school in Georgia to Georgia Tech, went from, they called the senior class Advanced Algebra and Trigonometry in my high school, and I went to calculus first quarter, Georgia Tech. No pre-calculus, trig, or anything else. It's just from Advanced Algebra and Trig to calculus. When I started reading that book, trying to read the book, I was calling words sometimes. I had no clue what it was talking about. And some days I'd say, I'm not even going to bother. So, because I felt like I was just lost. But then I realized that when I was in class, the day after I had read the thing, what the professor was saying kind of made some of it make a little more sense. But on those days I didn't read before I went in, what he was saying was just as confusing as what I had read, if I had read it before, but couldn't pull it together. So every exposure you get to something goes better. I'll make a confession here. When I started teaching physical science, I had taught physics for years. I'd had lots of physics courses, but I'd never had an astronomy course in my life. And when I opened the first physical science book, there were 3 chapters in astronomy, which I knew nothing about. So I took that book home, and every night I'd read in that book wherever I left off in class for as far as I could read and still make any sense out of it. Always that covered the next day, but I would do it every night, the weekend too. And when I finished, I'd go back and start reading again. I must have read every one of these chapters a total of umpteen times, I don't know, 3, 4, 5 times, before finally it all kind of started coming together, okay? Now, I really enjoy it now, but really, for it to make sense, you have to read it at least once. Listen, okay. So the summary is here. Once you've read the chapter, this is a very short summary, but it has a lot of words italicized, which are your most important words, okay? There's a summary of the equations. Don't worry about that. That has some math that we're not going to do. We did do the second equation. I'll mention the third one. Okay, then there's the key terms. These are listed alphabetically, but they do give the page numbers where they were first introduced or talked about, defined, or whatever. It's a fairly short list of key terms, but they're largely those words you found in italics in the summary. In my mind, the very best thing to study for your test is applying the concepts. There are 50 questions here. That's maybe a few more than average. They're all multiple choice, all have 4 option answers. If you can do these, the answers are given. I would do them first and then look at the answers. Any you missed, see if you can figure out why you missed. If you can't, ask me and we'll talk about it, okay? That, to me, is the best thing to study for your test. So if you have those, good thing to use. Now, then there's questions for thought. There are 21 of these. That's more than most chapters have, even though the summary is pretty short and stuff like this. For further analysis, 5 is about average. And then there's some parallel exercises. These are mostly like the examples, those few examples we did, those equations, formulas. Don't worry about those, okay?
And you said that don't worry about the questions for thought either?
No, questions for thought are good to look at, and the for further analysis are good. But the best things are the applying the concepts, which are multiple choice questions. A lot like the questions you'll see on your test. Not the same questions, definitely not, but just approach from a different direction. If you understand these, you'll probably understand most of the questions on the test. Your test is going to be no more than 20 questions. This is 50, so this covers a lot more. What's that? What's that? Is it 3:45? My goodness, what perfect timing, huh?
Yes.
We just finished the chapter. We'll begin next time with chapter 15, which means I'm almost certain we will not finish chapter 15 to have a lab next time. So we'll just, we made chapter 15. We won't finish it in 2 hours, I don't think. It took us more than 2 hours to get this chapter 14 done. So we'll start with chapter 15 and go from there, okay? Which means we'll probably go 4 hours and 15. We may finish in that time, but there won't be time for a lab. And then the last 30 minutes will be your test on chapter 14, if you choose to take it. Okay? Then the next Tuesday, we'll finish Chapter 15 in time for the lab, but we won't have its test until Thursday. So I never want to test you before you've had a chance, after we finish the chapter, to do. The lab could be the same day or the next day. It doesn't matter. Okay. So I made a mistake here. Let me end this and pull up my disk and yeah. All right. Now, do you need a little break before we get going on labs? I thought so. Okay. If you need one sooner than that break, we can always take one. Okay. So let me go from this slide, current slide, and I'm going to pause the recording. All the lights coming on. Coming up on Wednesday, February 12th and Thursday, February 13th are college transfer days. And the 12th will be on Birmingham campus from 9:30 to 11:30. It's the B Hall, the academic hall. And then on Thursday, it'll be here on this campus, down, I think, in the faculty staff dining room. I don't know that for sure, but in this building, faculty staff dining room. There's a whole bunch of schools have been invited to come. I won't read through the whole list, but if you want to see them, they're here. I mean, just about every major four-year school in Alabama, several, and there's some from Tennessee, Kentucky, Alcorn State, West Georgia, just Mississippi State. There's a bunch of them. Okay, and there's also these things called research opportunities for undergraduates, research experience for undergraduates. And this is at one of three campuses, University of Illinois, Arkansas, or Howard University, and they're looking for to recruit minority engineering students. So if you are one or you know of one, please come get this information and follow up on it. Okay. Now, let's start with the lab. Did everyone get a copy of the lab? Okay. Now, hopefully you've read the first page, okay? You may not have, but let's go through a few things. Let's first talk about, remember what your local meridian is. We talked about this last time. If you weren't here last time, this may be sort of new to you. If you were to face due north, I think I'm about due north here, and go from the due north of the horizon directly overhead, and then go to due south on the horizon, that's your local meridian, which I just have traced out there. That's your local meridian. Now, when the sun or any other object in the sky crosses that meridian, say the sun earlier today crossed somewhere probably about like this. When it crossed that meridian, your local meridian, we said it was in transit. It transited your meridian. By the way, that's the highest peak the sun will have that day. Is the highest it gets in the sky above that southern horizon will be when it crosses your meridian. Also, before that, it's on its way up, and after that, it's on its way down. Okay. Now, when you're talking about the celestial sphere, remember it's really a hemisphere, it's a bowl we were picturing above us. If you were to trace the various stars or other things around it, you find out they make one complete revolution about every 24 hours because we're spinning once every 24 hours approximately. So just little things to keep in mind. Now, Tarsha, right? You look pretty bright. I'll let you be the sun. Okay? Now, if I'm here, and there's my due north here, and you're over here, I can see stars that, okay, let's turn my back to you so it's nighttime, and I see the stars up here, okay? Now, screen is doing weird things. Okay, I was afraid the power was going off. Okay. If I were to track a star that is rising, because I'm spinning, remember, and it rises and then sets, and when it comes back to the same position, that's about 24 hours away. Okay, I can see these stars here. But then sometime later, it's going to be hard to picture too much, but let's just say, when finally I turn to your rising, the stars that I was seeing directly over there before you turned so you rose, those stars now are going to be blocked by you. We are said they are eclipsed by you. The eclipse, an eclipse, is when the sun and the other object line up perfectly with the earth. For instance, say a lunar eclipse is when the moon is here, it's reflecting light from the sun, but when it gets in the earth's shadow of the sun, you don't see it anymore. That's a lunar eclipse. A solar eclipse, and we'll talk about this in later chapters, when the moon gets directly between me and the sun, then it blocks the sun. Well, the sun also eclipses stars. The stars right back yonder, the sun gets in their way. So there's some star back there. But you see, I'm not just spinning, I'm also moving around the sun, right? Sometime a year I'm further from the sun, sometime I'm closer. Now the sun's blocking those stars back there, where Justin's sitting. Before, you were blocking the stars back there, eclipsing those stars. So if I took all those stars and mapped out the ones that are being eclipsed from the sun, as I move around the sun, then all these stars would move. And those, as I move around, you're eclipsing various stars. That pattern of stars is called the ecliptic. That's the plane that's formed between the sun and the earth, and that whole plane, that circular plane there, that would be the eclipse. Okay? The sun creeps from west to east at nearly uniform rate, taking 365 days approximately for me to make my trip all the way around the sun, for the sun to eclipse all those different stars. Okay? About 365 days at almost 6 hours. Now, what comes out of this almost 6 hours? Every 4 years we have a leap year. We add one more. We call 4 times 6 is 24. So we add another day. We'll talk about that in a later chapter 2. Okay? So, that was your page 1. Or actually, page 359. Okay? Flip over one page and we'll do part A, the celestial pole and the equator. Okay? Now, I'm going to draw this same type figure several times, so hopefully you'll get used to seeing it. I'm going to place our good old Earth. I think I'll close this book because I don't want to damage my DVD, CD, or whatever. All right, here's going. Oh, let me. Okay. Now, I'm going to pull out my handy-dandy visual aid. Okay? We'll talk about this more later, but for right now, this will be it. I think we mentioned this before. You notice anything about that? It's tilted. Okay? That's going to be important, even more so in the next couple chapters. Okay? But for right now, what we'll deal with is the fact that if I'm located on my globe here, right here in Birmingham, Alabama, that's it right there. Okay. And if you put that as right, like this, then the equator, we are about 30, I never remember these numbers well, 36 degrees, 24 minutes and so many, 45 seconds above the equator. That's our latitude. Okay? Now, if you're somewhere else, you have a different latitude. Somewhere else, a different latitude. So you have various latitudes, and that's what we're going to be drawing first. Okay? And that's why I wanted to get to this globe so you have at least a clue of what I was talking about. So I'm going to draw a little globe down here. Okay? That's the Earth. Okay? Pretty small Earth, right? And here I am standing on the Earth. Okay? Pretty big guy, huh? Okay. Now, this is my horizon. Okay? This is all I see. I don't see the stuff below that horizon, I only see the stuff above. Now, let's just say this is where I'm standing, and let's say that is my equator. Okay? The Earth's equator. My latitude is this angle right here, alpha. Call alpha. No, that's something else. Okay. That's my latitude, alpha. Now, the celestial sphere is drawn like this. And let's do the line directly overhead from me. That's called my zenith, the top point directly over my head. This is the local meridian. Remember I talked about that from due north to due south. So here's due, actually this is due north here, and this is due south there. Okay. Now, remember, you have a, oh, and by the way, if I drew a line perpendicular to this line, the equator, and this is the equator here, remember? And the equator goes something like this, like that. Well, if I draw a line okay. Let's first take the angle alpha, okay? This angle alpha, this is what we call the celestial equator. This is the actual equator on the globe. This is celestial equator on the celestial sphere, directly above this equator here. Okay? Now, what would this point over here be? The North Star. Did someone say? Perfect. That's called the North Star or Polaris. Directly perpendicular to the celestial equator. Yes? What does what? One.
What does Polaris mean?
Polaris? Pole star. Okay? Pole star or North Star. Pole star. P-O-L-A-R-I-S. That means pole star. I don't know how they got Eris out of it, but they got it. Okay. Now, I think I've got everything there that they're supposed to. This is 90 degrees, 90 degrees from the North Pole. This is the North Pole here. There's the equator, 90 degrees between those. We're here at latitude alpha. Now, what you're asked to do is prove that the angle alpha, the observer's latitude, is in fact the same as the angle alpha of the north celestial pole over the northern horizon. So in other words, we're trying to see, is this angle here also alpha? There's the question.
Yes.
Why? Okay? You're right, it is the same. Here's why. Remember, this is 90 degrees. This angle here is 90 degrees from the celestial equator to the North Star, right? So this angle in here has to be 90 minus alpha, because subtract alpha off of it, and this is 90 minus alpha. Okay? Now, the angle between your zenith and the northern horizon, that's also 90 degrees. And if this is 90 minus alpha, that means this one has to be alpha. call alpha. Okay. That indeed is. Because the difference between these two is 90 minus alpha. The difference between these two is 90 minus alpha. That means this must be the same as that. They're both alpha. Okay. Now, what they did, rather than saying 90 minus alpha, they called this angle theta. Okay? Theta is 90 minus alpha. Okay? Because this is 90 degrees here. This is alpha. That would be 90 minus alpha. This would also be theta. Okay? And then there's just no way that if this, and this is the same angle here as this angle here. And this angle plus alpha must be 90. This angle plus something must be 90. That something has to be theta. So any way you can express it to indicate to me that you understand why this is true.
So just so I can put this in words on the paper, how would you want to do it?
Okay. You can use symbols too. You don't have to write out sentences. You can just fill in the sort of what I've already done. The book called this theta, and from that you can fill in the rest of it pretty much like I did. Okay? Now, yes?
Can you spell what the book called the graph?
Oh, the book calls what?
Can you spell
Say,
This thing right here? Theta. 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 It makes the E sound like a long A. And the A sounds like a short A. Okay. Theta. It's Greek. Okay? Now. Pheta. All right. All right. Now let me give you a very practical application of that. Okay? Remember I told you last time how to find that North Star, right? You find the Big Dipper, and the N2 stars on the Dipper part are called the pointer stars. They point straight toward, or very closely straight toward the North Star. North Star is not a very bright star, but if you use that, it's the only star it's really pointing to with any brightness at all. Okay? So that's the North Star. So if you find that North Star, and I was in the Navy, okay, we had to do what they call celestial navigation by the stars. We use various stars, and you have to enter a lot of books and have to do that. But you really wanted to know that North Star. Why? Because when you got the sextant and you were shooting the stars, you went from the horizon to that North Star, whatever angle that was, that's your latitude. So if I found out that was 30 degrees and we're in the middle of the Pacific Ocean, somewhere north of O'Hara or whatever there, let me see if this is 30. I think that's 15. 30 would be right there. Now, somewhere north of that, then I knew I'm right on that line. Somewhere there. Do some other stars, and you get an X, and you find out right where you are. Yeah?
You say you're on the southern portion of the Pacific, below the equator.
If you're on the southern
How
hemisphere,
can you,
there is no South Pole star.
I know, but how can you navigate using celestial?
Okay. You find other stars, and you find the line that you're on. They won't be along the latitude line if you find the other. The North Star, whatever you find that to be, that's exactly your latitude. So that's a practical application of this. Nowadays, we use satellite navigation. People don't shoot stars anymore. Back when I was in the Navy, that was, in fact, we just got the first sat nav put on our ship, and we were still testing it out when I left the ship. So I was in a little bit of modern error, but not too much. Okay. Now, here's another question. If the celestial pole makes an angle of 40 degrees over the northern horizon, there's the pole star, And this is 40 degrees over the northern horizon. So let's say that alpha is equal to 40 degrees. Now my picture doesn't look like it, but let's assume that it is. What angle over the southern horizon does the celestial equator make? Okay? What angle over the southern horizon does the celestial equator make? And what would that be? 50, because it's 90 minus alpha, which is 40, and that would be 50 degrees. Okay, do you see that? Okay, so that's number 2 on page 361. Now, suppose you are in Quito, Ecuador. Okay, does anyone even have a clue where that is? Okay. All right. Wait a second. You got it. Because here's Ecuador, E-C-U-A-D-O-R. In Spanish, guess what that means? Equator. Exactly. That country sits right on the equator. Now, many other countries do too, but that one's named Ecuador. And if you're in Quito, which is the capital, they show it right on the equator. I mean, it's not exactly, but part of the city is on the equator. Exactly. Okay? So you're in Quito, Ecuador. Okay? The question here is, and here you are standing at Quito, Ecuador. It says, suppose you're at Quito, Ecuador, latitude 0 degrees. Where is the celestial equator? Say again? Yes, it starts here and goes directly overhead this way. Your local meridian is this way, but the celestial equator is exactly perpendicular. It goes directly overhead, east to west. So there's that answer. Directly overhead, east to west. Okay, I didn't want to step on it. Okay. So that's number 3. All right. Now, the ecliptic. Remember, I mentioned that from the first page. The ecliptic is a circle on that celestial sphere that is tipped at an angle of 23.5 degrees. What do you reckon the 23.5 degrees is? That's the tilt of the Earth. If you see down here, okay, this is 90 down here, subtract 23.5 from it, and you get 66.5. And that's right where we are, 60. 1, 2, 3, 4, 5, 6.5. That's it. That's where the 23.5 degrees, that's the tilt of the Earth to the path around the sun, so we're at an angle of 23.5 degrees to that plane. Okay? Now, let's go back to the celestial equator. I won't redraw all this, but if you got it, you got the thing in front of you. Here's the Earth sitting there. North pole up this way, south pole that way. There's our equator around there. Expand that outward. There's the north celestial pole. Somewhere up there is the North Star. Here is your south celestial pole down here. There's no stars there. It's blank space, okay? The celestial equator is outside of the actual equator, but that's not directly overhead. This is the ecliptic. This dotted circle right there is the ecliptic. That's the path the sun goes around. Actually, it stays still, but that's where we go around the sun. That's the ecliptic. Okay. Now, what happened back on around December the 21st? Yes. A little out of.
It was the shortest astronomical day.
Okay, the shortest amount of daylight. All the days are about the same length, but the shortest amount of daylight. And why is that? Because we were down here, they call that day the winter solstice. Because in the northern hemisphere, that's where the sun is the furthest down in the sky. So it takes less time to go up and come down, shortest amount of daylight. Okay? However, if you were down in Australia, that was the longest amount of sunlight. And what's been happening in Australia? Fires. Why? It's the dead heat of summer down there. This is like their July, okay? And they are burning up, literally. Huh? What? Animals? Oh, yes, amazing. And my wife, a really dog lover, she said it was so sad, the Australian shepherds that keep up with the sheep and cattle and stuff like this, they kept with them, and they could have run and gotten away, but they stayed with the herd. And they vanished. Just really sad, but they're that well trained over there. Amazing. Okay, but anyway, that illustrates what's going on. Coming at about March 31st, what is that going to be? How about March 21st? Vernal equinox. Now, what in the world could equinox mean?
Equal in amount, straight up and down.
Say again?
Is it when the Earth is straight up and down?
Okay, not quite, but pretty close. What it means? Equal, nox, night. Equal day and night. 12 hours of daylight, 12 hours of darkness. Where? Everywhere on the globe. The vernal equinox is that one in spring coming up, March 21st, around there. That would be our vernal equinox. Now, coming up then around June the 21st, what's that? Summer solstice. Now, what does solstice mean? What's this SOL mean? Solar, sun. And stis means still. Okay, and what we mean by that, every day, right now, every day if you went out at noon, exactly at noon every day, when the sun crosses our meridian, when it transits, it's going to be a little higher in the sky. A little higher in the sky. Every day, just a little, not much, just a little higher in the sky until the summer solstice it stands still. Sun stands still, solstice. And then after that, it starts dropping again. Okay? Now, so what was it called back on December 21st? The winter solstice. Okay. Now, they used to always have big parties on the winter solstice. And you know the reason why? Because there was a great fear that the sun, every day coming up to the winter solstice, it got lower in the sky, lower in the sky, lower in the sky. And they were afraid that sometime or another it would just keep dropping and never come up again. So when it started changing and going up again, they partied, okay? Because, yes, we're going to have another year. Okay, it seems a little far-fetched, but it is. Now I don't mean to sound heretical or anything, but what else is close to December the 21st? Even closer. Say again? Even closer than New Year. Christmas, exactly. Okay, I thought someone said it. I don't hear well. Okay? And guess what? Okay? This sounds terrible, but it's probably true. The shepherds wouldn't be out in the field at night in the middle of winter, near the coldest day of the year. Okay? They just didn't do it. They'd have the sheep inside, keeping them warm. But because that was already a big party time, they said, let's make that Christmas when we celebrate what really matters. So, what's that?
They got it from Yule. They started celebrating Christmas from Yule.
From
Yule. It's a pagan holiday.
Oh, yes, exactly. And that's why the pagan holiday. That's when they started celebrating because the sun quit falling and started going up again. And that's pretty close to the truth. Okay? Because they wouldn't have been out in the field by now. Okay? Not in the dead of winter. Okay? Just wouldn't have happened. Okay. But everybody celebrates, even the pagans. I mean, Japanese celebrate Christmas even though they're not Christians yet. I mean, so everybody celebrates. Okay. But you're right. It came from that. All right. So anyway, I think that's most of what this figure is telling. That angle between the ecliptic of the sun and the celestial equator, that's your 23.5 degrees, the tilt of the Earth. Okay? Oh, and then back around September 21st, what do we call that?
The
Autumnal equinox. And why do they call it equinox?
the same.
Equal day and equal night. You're absolutely right. In German, nox is night. Okay? Still not. Okay? Now, the figure here on page 362
This is on the A part here is the summer solstice. The celestial equator, if I'm at, let's just say 30 degrees north, that means this will be 60 degrees. There's our celestial equator. When the sun's above that, you're in summertime, or you're moving toward that. And it's below that, you're moving forward or away from wintertime. And that's what these are showing. The sun is maximum time because it actually rises north of east and sets north of west. So it's up for the maximum amount of time on the summer solstice. Where in the winter solstice, when the sun is lowest, it rises south of east and sets south of west, shortest time that it's up. Okay? Now, our house happens to face due south. Okay? And on the north side of our house, there's the bathroom window, and I drive my wife crazy. Every day I go in and open blinds in the morning and close blinds at night. And the blind in the bathroom on the north side, in the middle of summer, the sunlight comes in. Now it doesn't, because the sun is too low for that here, where it rises and sets north of east and west in the summertime, south of east and west. So it's no way going to be coming in morning or evening. Okay. Now, here's a few terminology things. We talked about something similar to this before, but this is a little bit different. Okay, and we're going to need these. Here we are on the Earth. We look up here and see a star in the sky. Now, if you use the Earth's equator here, this then is the celestial equator, right? The angle between the celestial equator and that object, that's called your declination of that object. Okay? The declination. Before we called it, from the horizon, we called it the altitude. We're not doing the horizon, we're doing the actual celestial equator. That's the declination. Now, the other angle you need is called the, and they're not showing it on this one, so I'm going to hold off on that until we get a better picture. Okay? But get the, oh, here it is. Next page. Flip it over to 363. Okay? Now, what we're going to measure here is how far along the celestial equator that object is. Now, we're going to have the object up here. Here's its declination, the amount north or south of the celestial equator. And what we call right ascension is from the vernal equinox. That's where the sun is on what day? Around the 21st of March. Okay? You go right from there, how many angles, the angle it is, that's called your right ascension. So where that line, that's from the object down to the celestial equator, how far that is. That's right ascension, always measured from the vernal equinox. Vernal equinox is where the ecliptic, the dotted line here, that's the path the sun is on, and your celestial equator. Where they cross in the springtime, March 21st, that's where you measure your right ascension from. Okay. So here are the terms. Declination is angle above the celestial equator or below the celestial equator. Positive above, negative below. Okay? And the right ascension is from the vernal equinox, what angle it is, to the place where that object is. Okay? Now, here's something that's a little unusual. You do measure that arc here in degrees, but they also measure it in hours of right ascension. Okay? So, what we're going to do is figure out, number 4 here, is how many degrees of arc are equivalent to 1 hour of right ascension. Okay? Now, I want you to picture, well, here it is, okay? There's your celestial equator. How many degrees are there around that celestial equator? All the way around. 360 degrees, okay? the sun or any other object, how many hours does it take to go around that? 24. So 360 degrees is equivalent to 24 hours. So I'm going to erase this. I'm going to come back and draw it again, but let's clear the screen here. And let's write down what you just told me. We have 360 degrees of arc, okay, is equivalent to, or the ratio of 24 hours of right ascension. RA is right ascension. Okay? Now, what's the ratio of that? Anyone got a calculator? 360 divided by 24? Second?
It's 10.83.
I don't think so.
360 divided by 24?
Yeah. 15, right? Your calculator gave a little bit strange answer earlier, too. You got the same thing? Okay. All right. So this is 15 degrees arc is equivalent to 1 hour of right ascension. Okay? And that's exactly what number 4 asks for. How many degrees of arc are equivalent to 1 hour of right ascension? Now, does anyone know what the next smaller unit of an hour is? Minutes. Does anyone know what the next smaller unit in a degree is? It's also minutes. They're not the same minutes. 1 minute is time, the other is a fraction. But guess what? There are 60 minutes in an hour. There are 60 minutes in 1 degree. Weird, okay, but it's true. Now, where did that come from? Blame it on the Sumerians. They were the ancient Babylonians, and they had a base 6 system. They used 10 fingers in toe, that gave them 10, but they used 6. I don't know where they got that. 6 times 10 is 60. And that's why there's 360 degrees in a circle. It's 60 times 60, okay? I don't know why, but that's how they divided everything up, okay? And that's why we're stuck with it. So now we want to ask the question, how many minutes of right ascension are equivalent to 1 degree of arc? Okay? Now, if it's 1 hour of right ascension, how many minutes is that? That would be 60 minutes of right ascension. Okay? Now, we're going to flip this over in a minute. So let's flip it now. So 60 minutes of right ascension is equivalent to 15 degrees of arc. The question is, what is that equivalent to 1 degree of arc? So how would we do that? Second, divide 60 by 15. And what do you get? 4. 4 minutes of right ascension is equivalent to 1 degree of arc. Okay? Yeah.
This is numbers 4, 5, and 6.
This is 4, 5, and 6. We just did 4. This is 5, and we're about to do 6. Okay? Now, the 6th question is, how many minutes of arc are equivalent to 1 minute of right ascension? Okay, so if this is 1 degree of arc, how many minutes is 1 degree? Say again? No, how many minutes of arc is 1 degree of arc? How many minutes in a degree? 60. This is 60 minutes of arc. Okay? I'm going to use the same abbreviation. Minutes of arc. I can't write.
minutes of arc is equivalent to 4 minutes of right ascension. So let's flip that over again for number 6. Have 60 minutes of arc is equivalent to 4 minutes of right ascension. So how many minutes of arc are equivalent to 1 minute of right ascension? That's the question, number 6. Say again? Say again? 15. 4 will go into 60. 15 minutes of arc are equivalent to 1 minute of right ascension. All right. So you just answered 4, 5, and 6. Okay with that? Making sense? Okay. Now, if you turn to page 364, we don't have a celestial globe, but we have something that's, in a sense, kind of familiar to it, similar to it, and that's called a star chart. Okay? Now, I'm going to sort of help you figure out how to run the star chart, and you'll see I have a string through the center, and then there's a hole down here. And what you're going to do is line up the string with the hole, and you'll read off things on that. Now, basically the hole is at the top, so we will sometimes flip it over like this. Okay? Now, most of the time we're going to be on this side. Okay? With the North Star being right here, and then the days and the times here. Now, because the words are upside down, I'll probably flip it over like this. But it's just flipping the thing around so you can read better. Okay. Now, it says locate on your star chart here. Well, don't worry about this top part. It says which stars are located in the following coordinates. Now, we start with right ascension. Where is right ascension measured from?
6 hours, 43 minutes.
The what?
6 hours and 43 minutes.
No, okay, where is it measured from? Where do you measure that from? Right ascension. Okay? Remember we did that a page back. Right ascension is measured from the vernal equinox. And when is the vernal equinox? March 25th. Okay? So what I'm going to do here, I'm going to line up these two holes, if I can get my fingers to work, and I'm going to turn this, right now it's on December something, so I'm going to flip this around, it has little teeth here you can do, to March the 21st. And there we are, March 21st. Okay? Now what's significant about March 21st? That's where the celestial equator, which is a solid circle here, crosses the ecliptic, which is the dotted circle there. And right there they cross on March the 21st. Okay? So this says March 21st, you're on the celestial equator. Now I'll do this first one, and it says we're, I'll flip my page so I can't read. The right ascension is 6 hours and 43 minutes. Okay, now, these are hours here. There's 12 midnight, 11, 10, 9, 8, around this is PM, AM is here. So what we're going to do is go 6 hours and 40 minutes. So there we're right on an hour here. So there's 1, 2, 3, 4, 5, 6 hours and 40 minutes is about 2/3. So it's somewhere right about, so you want to count again. 1, 2, 3, 4, 5, 6 and 2/3. I'm going to call that July 1st. It's something pretty close to that. June 30th, July 1st, something like that. So I'm going to roll this around till July 1st is right there. Okay? There, I'm right at July 1st, right there. Now, the next thing it tells us is declination. Now, declination is always measured from what? Flip back to the previous one on page 362, bottom of the page. Huh? Okay, but what is measured from? The celestial equator. You see that on page 362, the bottom illustration? Celestial equator. Now, when it says minus 1639, 16 degrees and 39, that means you're south of the celestial equator. Remember, this circle here is the celestial equator. Now, to get an idea what your measures are, if you're going from here to here, that's 90 degrees. So halfway would be 45, and half of that would be 22 and a half. So it's something, this is minus 16. So let's start looking for some bright star that's south of the celestial equator, about 16 degrees, wasn't it? 16 degrees, 39 minutes. There I see a star. What star is that? Can anyone read it? You probably can't. It's Sirius. Are you serious? No, okay, not that serious. It's Sirius. 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 And if you remember, when we were talking in class last time, that is the brightest star in the night sky. Sirius. Okay. Now, who wants to try the next one? I showed you how to do it this. Okay. Here we have the next one. Now, I'm going to fade in and out of sound here, but I'll try to talk loud enough that we know pick it up. Okay, where do we start from?
We start from the right ascension.
Right ascension, but where is that measured from? Actually, probably better to flip it, like that. So, what I'm going to do is turn on this so it's easier for him to read. Where do we start? What is right ascension measured from? Vernal equinox. And when is the vernal equinox? Vernal equinox is when? March. So flip that around until March is down here where that string. So there's the T. Yeah. Good deal. March the 21st. What's true about vernal equinox? What two things cross? The ecliptic is the dotted circle, and the solid circle is the equator, and celestial equator, and you see they cross right there. Okay? Straighten that up. There we go. So you're going to go 6 hours and 22 minutes right ascension. So this is right on an hour. Okay, go back to March 21st. Okay, let's put line up down here. That whole line up. 21st of March. It's right there. Okay. Whoops. Right there. Yeah. Okay, right on the hour. 1, 2, 3, 4, 5, 6 hours and 22 minutes. That would be about a third of an hour. And about a third of an hour would be what? Maybe the 25th of June? So flip that down around the 25th of June. Okay? Now, the declination is what? Okay, that means 52 degrees, 40 minutes south of the celestial equator. Remember, this was Sirius over here was minus 16. That's somewhere below our horizon. So flip over, flip over, flip over, flip. Good. Yeah. Let's see if we can find, this is the southern hemisphere here, and yeah, I think it may be this one, right? No, that's Sirius. Okay, 50 degrees. I still don't think we can see it. It's below our horizon. We can't see it. So basically, the star name, we don't know, but it's somewhere close to the constellation Columba. Columba. So what you can put, it's south of Columba. Columba.
BA. We don't see that constellation because it's south of us. It's below high horizon. So he had an easy one. There's no star visible on a star chart. If we had a celestial globe, we would be able to detect it. We don't. So our star chart only code shows a little bit below the celestial equator. So who wants to go next? All right. Go. Okay. All right. We're looking for right ascension, 18 hours and 35 minutes. Where do we start right ascension? Say again? Vernal equinox, which is about what date?
March 21st.
Yeah. So I found it easier to put this over the roof. Okay. This way. Okay. And line up the two holes there. Just holding that hole in the string. Sort of tight. Okay. And start at March 21st. What's true about the vernal equinox? Okay, that's true for what?
It's the line.
The celestial equator and the ecliptic line up. And there's the celestial equator is that circle there, the solid circle. The ecliptic is the dotted circle. You're right on. Okay? Now, we go 18 hours and 35 minutes. So each one of these little things here is an hour. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 35 minutes. Just 18 and a half. Pick a date close to that. Yeah, December 25th. Let's just turn around to December 25th. What's the next thing to give us? The acclamation, and what's that? 3844. Okay. Positive meaning it's going toward the North Star, going to the north. North Star is right here. So it's about a third of the way from the equator to the North Star. Oh, that looks like it could be something right there. Vega. V-E-G-A. Okay? That third star name is Vega. V-E-G-A. All right? Good deal. Who wants the next? You already done it. Huh? Okay. We're given right ascension first. How do we measure right ascension? From the vernal equinox. When is the vernal equinox? Okay. I like the Let's bring everything. Not everything. Okay. Now, we want to, we're in the vernal equinox? March 21st. Okay. Spin that around. Oh, no. Spin this way. Yeah. Keep the holes lined up. And then turn that around to March 21st. What's true about vernal equinox? What two things line up? Ecliptic and the celestial equator. They almost sound the same, but they're not. Okay, and you see the celestial equator is the solid circle here. The dotted circle is the ecliptic, so you're not quite on the 21st. So you need to go a little bit further. Let's see, 16, 17. You're holding awfully tight. Okay, yeah, 21st. Just past, right here. Yeah. Okay, right there. Yeah, so it's lined up right there. Okay, and what is your right ascension? 5 hours and 12 minutes. So here are the hours. 1, 2, 3, 4, 5, and 12 minutes would be just a little bit beyond estimated date there. June the what? 9th. June 9th. We'll try that. So twist June 9th down so it's lined up with your holes. Okay? And we are minus 8 degrees and 15 seconds. Here's the celestial equator. So just below that, oh, there was a bright star. What's one of that? Rigel. Rigel or Rigel? R-I-G-E-L. Rigel or Rigel. That's the fourth star. R-I-G-E-L. Pretty bright star. Okay, who's next? All right, here we go. Where do we begin?
So we got, okay, 7 hours.
Okay, how do I write a sentence on what day? Okay, we put that around to March 21st.
Oh, yeah.
All right, I get you. That's and 7 hours and 37 minutes, write a sentence. There we go. 1, 2, 3, 4, 5, 6, 7. And 37 minutes. What day? About the 11th. Yeah, 10th. Okay. You like it? You quit. You like that down here.
No.
Things like that, those classes that like you want to go to
You like that?
So, and like they left like, so in the grant
You like that?
3 to 4
Okay, and where are we? 5 degrees.
Yeah, me too.
Second. North, yeah. We're going toward the north side, north, and I'm guessing it's that probably. What's that star name? Okay, yeah, that's the constellation. This is a star. Procyon. 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 That's the 5th star. Procyon. 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 That's the star name. Okay? All right. Procyon. Procyon. All right. Now you're doing right essential. Where do you measure that from? Where do you measure it from? What? Okay. Where do you always measure right ascension from? The vernal equinox. When is vernal equinox?
March 21st.
March 21st. So you twist this around, get the holes lined up. The holes lined up. This hole is up. Okay, good. Okay, and twist around to your March 21st is on that line. All right. It's moving. If you will, don't hold it quite as tight, it makes it easier to turn. All right, good. Okay, twist it all around. Twist it on. Now, no, okay, be sure you line up your holes. There, twist on around March 21st. All right, what's true about vernal equinox? What two things cross? The celestial equator, which is a solid circle there, and the ecliptic, which is the dotted circle. And sure enough, you're right on it right there. Okay? Now we're going to go 14 hours and 36 minutes. Every one of these little silver things is an hour. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So about 14 and a half.
Okay, so you're doing these by these hours.
Right, exactly. So 14, that's 12, 13, 14 and a half. Just pick a date there that represents that. Right. October 27th. So, right. Halfway between. Okay, October 27th. Twist that around so that's that. October 27th. Yeah. Now, if anyone had looked too far ahead, you already know the answer, I think. But we'll see. October. What day were you going to? 23rd. Okay, you're 7th. Is that right? Okay, yeah. Now, what is your declination?
60, negative 60.
Negative means south of the celestial equator, but you don't see south of it. So flip it over. You flip it this way. Flip. Okay.
Oh.
Okay.
Okay.
All right. Back to October wherever you said, 20, 27. Line up your holes. You're all over there. Right there. Put it out over 27. Now you're on 23rd. That's somewhere around there. But guess what? South of the celestial equator, here's the celestial equator here, you still can't see 60 degrees. However, you know it's something south of Centaurus. Centaurus. Something south of Centaurus. Centaurus is a constellation, is some star south of that.
Spell it one more time.
Centaurus. Okay? Anyone know what a centaur was? Yeah, man in front and a horse behind, sort of. Something like that. Okay. We've done our stars. Now let's go down to what constellations are located at approximately these positions. Who wants to go first on the constellation? You've done it. You've done it. Anyone who hasn't done it? Okay. Okay. Where do you begin?
March 21st.
Okay. All right. What's true about March 21st? Vernal equinox. And what's true on the vernal equinox? Celestial equator, which is a solid circle, crosses the ecliptic, which is a dotted circle. There you are, right on. Okay? What is the right ascension? 11 hours. So start your hours here, and those little silver things represent hours. So count 11 hours from here. Going this way. Leave it alone. So I count 1, 2, 3, 4. These little. Here, 1, 2, 3, 4. Right up there at 1 o'clock. Okay, find the date near that. September 4th. Twist that around to your circle. September 4th. Okay. Now, the declination is what? 50 degrees. How is declination measured? From what? Celestial equator. Celestial equator is that solid circle, and 50 would be more than halfway up. It looks like more than halfway up is Leo Minor. Okay? Anyone know what Leo stands for? The lion. And minor means small, so this is a little lion. There's also a big lion called Leo Major. Okay? So this is Leo Minor. Okay? L-E-O, huh? Oh, okay, got it. All right. Who wants to go next? Next constellation. Okay, just next door there. Okay. Where do you start your right ascension from? Vernal equinox. And what day is that? March 21st. So twist your thing around to March 21st. About 4 ways you can get it twisted around. I won't hold this too tight here. Okay, yeah. Hold down there. Twist it on March 21st. What's March 21st called? Vernal equinox. What's true about vernal equinox? The ecliptic crosses the celestial equator. You got to keep going. March 21st, you need it down here. Okay, right there. That's where the celestial equator, which is a solid circle, crosses the ecliptic, which is a dotted circle. There it is, right on. Okay? And you do 19 hours of right ascension. Now here are your hour marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 would be right there. Pick a date real close to that. January 5th. Twist that around so that's down there. Yeah. January 5th. And then your declination is measured from where? Celestial equator. And this is a minus 25, so it's south of it. Now, positive 30 would be somewhere about, this is 45, that would be 30, 25 would be there. Wait, I'm sorry. Let's go later. 45, 30, 25 would be there. So just below there, which I'm not sure I see a constellation. Probably this one, Scutum, S-C-U-T-U-M. Constellation Scutum. I don't even know what that looks like. S-C-U-T-U-M. Let me get back to our people who are not here can follow this. The second constellation looks like it might be Scutum, S-C-U-T-U-M. Okay, who wants to go next?
Me.
Again, you've already done it.
I haven't done that part.
No, we want everybody to get a chance.
I want
Tiffany, you were selected. Good volunteer. Okay. Now, where do you begin? March 21st, which is the vernal equinox. Line up this circle with that circle. Straight. Okay. And you put on that date, March 21st. Leave this line up. Okay, line up. I'm turning a circle. So March 21st is right on that line. What's true about March 21st? Keep a little bit further. That's 19. Okay, leave it right there. What's true about there? Your celestial equator, which is the solid circle here, crosses the ecliptic, which is there, and sure enough, it's right there where it crosses. Okay, and how do we measure right ascension from there? Hours. 1, 2, 3. Now pick the date represented by that little 3. May the 4th, isn't it? This little arrow here. Okay, May 4th. Okay, twist May the 4th down so it's at your line. Okay? Now, plus 20, what does that mean? 20 degrees north of the celestial equator. Well, that circle there is the celestial equator. That would be 45 because it's 90 here, 45 there, about halfway there. Be somewhere there. What is the constellation there? The question is probably Aries. Okay, number 3 constellation would be Aries. Isn't that spelled A-I-R-E-S? Okay, Aries, A-I-R-E-S. Who's next? Someone who hasn't done it. No, you've done it?
She has it.
Okay, you got volunteer. You can kick them if you want. Okay. All right, where do you start? Where do we start? March 21st, vernal equinox. Okay? All right, good. And what's true about vernal equinox? That's where the celestial equator, which is that solid circle there, crosses the ecliptic, the dotted, and you're right on it. Okay? And then you go 1 hour, right ascension. So go to this first thing there. Don't move it. No, go back. March 21st. March 21st. Okay. Okay? Go to that, and what date is right on that first hour? April 5th. Now twist April 5th around to your line. Okay? And then you go plus 60. Now the 60 is measured from your equator, celestial equator, north because it's plus. So here's your celestial equator. This is 90, so 2/3 way up there. What is the constellation there? Right there, I think. Up here. This one. Cassiopeia. Cassiopeia. C-A-S-S-O-P-I-O. Cassiopeia. C-A-S-S-I-O. Let me spell the rest of it. C-A-S-S-I-O-P-E-I-A. Cassiopeia or Cassiopeia. Now, from what I understand, from having been at the planetarium before, she was a very beautiful woman that wouldn't fall in love with this god or something like that. So he changed her to a throne and threw her out in the sky, and that's where she sits forever, or something like that. It's a weird story. Okay, so there was that one. Cassiopeia, C-A-S-S-I-O-P-E-I-A. EIA.
When you're doing a negative, you're going south, right? South.
Second,
When you're doing a negative,
you're going south, south of the celestial equator. Absolutely. Okay. Who wants to go next? Someone? Oh, you've already done it. Oh, I see. You volunteered nicely there. I'm sorry. Okay. Now, where do you begin? March 21st. Line that up. There you go. What's true about March 21st? Where the celestial equator, which is that solid circle, crosses the ecliptic, which is dotted, you're right on it. Okay? 13 hours right ascension. 1, 2, 3, 4. 12 is there. One more will be 13. One day replace that. October 5th. Of course, October 5th around is there. Okay? And then where do we go for declination? South 50. Hey, 50 would be right about here. North, you don't have to flip the thing over. Okay, it's 3 on October 5th, yeah. And here we're going south. Maybe Centaurus? I believe that's it. Centaurus! Remember the star was in that earlier? Centaurus. Centaurus. The horseman or man horse or something like that. All right. Number 6 here of the constellations. Who's going to go next? Have you already done it? Oh, you haven't? Okay, by all means. Okay? Where do you begin? Okay. Line up your line. Okay. March 25th. 21st. Huh? Yeah, spin it so you can get it. About as far away as you can get it. Not a ways to go. What's true about March 21st?
That's when the celestial equator is
Okay. Line up your hole. Hold the string hole. String. Hold the string hole. 2 holes. Okay. Okay. You see the celestial equator is a solid circle. The dotted line is the ecliptic. Right on it. And then you measure how many. What right is it? 7 hours. Each of these is an hour. 1. Like this. Like it.
But like, if you want to fix it to work, you just gotta log in.
Alright. Now, what is your declination?
negative 40.
Okay, I don't think we're going to see negative 40. So 40 degrees would be about right here, and you don't have that much south, so we'll flip this whole thing over. Keep it on what day was it?
Sorry.
July 5th. Okay. Go back. Yeah. Oh, so you can line up the whole. Get back to July 5th. Okay, you're right on. And let's see, 40 degrees south. Let's see, this is 40 degrees south. I believe you're probably Okay. It's called Puppus, P-U-P-P-U-S. I don't know what that, no, P-U-P-P-I-S. P-U-P-P-I-S. I-S. Puppus. The last constellation, P-U-P-P-I-S. All right. Now, I'm going to turn off a light again, I think. Oh, maybe not. Okay. All right. It says here in Part D,
it says, on the ecliptic, locate the position of the sun on June the 21st. Okay? So here's what we do. You line up this and put it on June 21st. Right there. June 21st. Okay? Now, it says locate the position of the sun. Where is the sun always? On the ecliptic. So there we are on the ecliptic. That's the dotted circle here, the ecliptic. Now, on June 21st, okay, I'm going to try to find something there. Okay, there's a little bitty star right there. And by the way, this is the Milky Way that goes through here. Okay? And there's a little bitty star just to the left of that. So it says, what's the question here? Does the sun rise exactly in the east on this day, on June 21st? Well, the sun rises when it comes across the eastern horizon here. So I'm going to twist this until June the 21st. That little bitty dot there is right on the northern horizon. I mean the eastern horizon. And it's right there. Does this rise due east? Here's due east. No, the sun is rising right there. Okay? So the answer is no. Okay? Does the sun rise exactly east on that day? No, it rises north of east on that day. Remember the sun coming in the windows when I open the blinds. Okay? So it's no, it rises north of east on that day. Okay? Say again?
June 21st.
That's, I couldn't hear what you said.
June 21st.
Yeah, right. That's the summer solstice. Okay? It says rotate the globe until the sun sets. Okay? So remember the sun. Remember the sun. It's this little dot right there. Okay? Right there. I'm going to rotate that until it sets. There it is at noontime. And I keep turning it and turning it until just before it goes below the western horizon. Okay? So keep going, keep going, keep going till just before it sets right about there. Okay? So I'm going to move this over here and see, is a question? All right, okay, I'm sorry I didn't read. Rotate the globe, blah, 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 blah. Bring the sun back to the rising position. All right. Why did he have me do that? I got to go back to the rising position. Sorry, I wasn't reading. Okay. Now, let me tell you one thing about that. Okay, there it is at the rising position, just coming above the horizon there. Now, here's a little bit of an error here. Okay? This is set up for 40 to 50 degrees north. We're not that far north. We're at 36 or so degrees north. So this isn't quite us. This is further north from here. In fact, where we bought this was when we went to Yellowstone, I think it was, and we were pretty far up there. So 40 to 50 was probably good for there. It says rotate it there. Bring the sun to the rising position by counting how many right ascension hour circles lie between the rising and setting points of the sun. Estimate to the nearest 15 minutes by the amount of time the sun is above the horizon on that day. So let me just read you a time. There is when it rises, and that's right there. It says right about 4:20. Let's call it 4:20. So it rises, so write this down somewhere in the margin there, 4:20 a.m. 4:20 a.m. Okay? Now I'm going to twist the sun around until it's getting ready to set.
That's going below the western horizon. So I've got a bunch of turning to go here. Okay, I've got to find the sun again. There it is. Okay. Whoops, a little too far. Right there. Okay. Line that up, and I've got about 7:40 in the afternoon, p.m. Okay? Now, the easiest way to do this, it rises, what time did I say, 4:20? Okay, a.m. And for my p.m., we said 7:40 p.m. Okay, this is probably a little earlier and a little later than what we would be here. But let's get this on a 24-hour clock. You would add 12 to that, right? So add 12 to 7 and you get 1940. Okay, let's subtract that. How many hours of daylight? This was sunset, and this is sunrise, and it's what? 15 hours, 20 minutes. Okay, so that's our answer. Okay, it says here, enter your estimate on table 1. So flip over one page here to page 366, and it says relative amounts of daylight and darkness at your latitude. We're using 45 to 50 at different times of the year. So June 21st, now here they have an error on all three of these tables. They say SEC of the sun. There's not an SEC. That is a DEC, declination of the sun. What is the declination of the sun on June 21st? We talked about it in class. Declination is how many degrees it is above the celestial equator. And how far is the sun above the celestial equator on June 21st? Say again? 23.5 degrees, exactly. So the declination of the sun would be, and that should be a DEC, not SEC, on all three of these tables, that would be 23.5 degrees, positive 23, 30 if you wanted to do it there, or 23.5 degrees. 23 degrees, 30 minutes if you want to do minutes, degrees and minutes, and positive, or you have positive 23.5 degrees, however you want to do it. Second?
Out of the 3-month period.
I can't hear you.
Out of the 3-month period.
Okay, no, just June 21st. Declination of the sun is 23.5 degrees north. Okay, on that day. That day only. Okay, what was the number of daylight hours? 15 hours and 20 minutes. Okay, so how many hours of darkness is that? Now I'm going to show you the easy way to do that. How many hours in a day? 24, but I'm going to put 23 and how many minutes? 60 minutes. Because 60 minutes is 1 hour, so this would be 23 hours, 60 minutes, that's 24 hours, and subtract from that 15 hours and 20 minutes. That makes the subtraction much easier. How many hours of darkness? 8 hours and 40 minutes. Okay, that's how many hours of darkness. Now this isn't actually where we are, but we're going to use this 40 to 50 degrees. Okay, let's go to December 21st. What's the declination of the sun on that day? Plus or minus? Plus is in summertime. Minus that's the winter solstice. So minus 23.5 degrees or minus 23 degrees and 30 seconds. However you want to say that. Okay, so what we got to do is find how many, when the sun rises then. So what I got to go is to December the 21st. December 21st is right about there. Okay.
That's the lunar solstice.
Okay, December 20, winter solstice. Exactly right. Okay, now I've got to find the sun then. Whoops, I can't see it on this one. I've got to turn over here. Ah, there's the sun. Okay, the sun here is okay, December 21st. Right about there. Okay. I've got to find the sun. It's on the ecliptic. Always the sun's on the ecliptic. And on this chart, there's a little square there. So I'm going to take the left-hand edge of that square and turn that around to sunrise. Okay? I've got to find, there it is. Turn that around to sunrise. Okay, right there. Okay, and this would be midnight. 1, 2, 3, 4, 5, 6, 7. Let's say 7 hours and 40 minutes. 7:40 in the morning. That's when the sun rises. Okay? The sun sets. I'm going to twist that around till we're setting the sun. And the sun sets, getting that little square there right on the horizon. And that would be can't read. 1, 2, 3, 4:20 in the afternoon. About 4:20 in the afternoon. So, did y'all record those? Okay, I'm going to clear my screen here to make it easier to do. What was the sunrise? 7:40. That was sunrise. And what was my sunset? 4:20. But let's make that's PM, so put it on 24-hour clock. That would be 16:20. Okay? Now let's subtract those, and what do you get? Now be careful when you're subtracting minutes. How many minutes are in an hour? 60. So you borrow an hour here, making it 15 hours, and add 60 to 20, and you get 80. Okay? Now, subtract those. This is 15, 80, subtract from that 740. What do you get? Say again? 8 hours and 40 minutes. Okay? That's how many hours of daylight you have on the winter solstice. Not very long. Okay? 8 hours and 40 minutes. Okay? Now, how many hours of darkness is that? How do we do that? You subtract this from how many hours in a day? Okay? There's 23 hours and 60 minutes in a day. Subtract from that 840. And what does that give you? 15 hours and 20 minutes of darkness. That's about what we got these days. We're a little bit less than that, but pretty close.
Okay, hold up. December 23rd. Okay.
Okay, December 21st.
All right.
Declination of the sun was
Negative.
-23.5, or 23:30. The number of daylight hours was 8 hours and 40 minutes.
8 hours.
And the number of darkness hours was 15:20. 15 hours and 20 minutes. Okay? March 21st. What's the declination of the sun? Yeah, you're going to be 12 and 12 hours. What's the declination of the sun on March 21st? It's what? 0! You're absolutely right, because the sun's directly overhead. Oh, wait. You're right on the celestial equator and the ecliptic are right on top of each other. So it's 0 degrees. So declination of the sun is 0 degrees, and the number of daylight hours and darkness hours are 12 and 12. Equinox, equal day, equal night. All right, now put on your jackets, folks. We're going to Altegard, Norway. It's what is it? What'd you say? 5:35? Okay, let's see what we can do in the next 10 minutes. Okay, here we are in Altegard, Norway. Altegard, Norway is latitude 70 degrees. So here we are, and we're in our heavy jackets. So we're all bundled up here in Altegard, Norway. Okay? Here is our horizon. And here is the celestial sphere. And we're at 70 degrees north. So here is the equator. This is 70 degrees. Okay? This is the equator. So let's draw our zenith here. Okay. Yes. Yes, sir.
Hey, sorry to interrupt that. Did you find somebody for that math class? Because somebody just told me my name was on it. That you said it was Tuesday, Thursday, in the evening?
Yeah, and Dr. Pruitt said you could do the hybrid type thing. I thought you wanted it that way.
Yeah, but I didn't know it.
Oh, I'm sorry.
I got back with you and let me know.
Okay, I'm sorry. It's been so crazy.
Okay. All right, so I'm
Yeah.
on the class?
Yeah. Okay, sorry. Is that okay tonight?
Yeah, we'll work it out.
Okay. All right, thanks. Sorry about that.
Okay, all right.
There's our zenith, directly overhead. Where is the celestial equator? It's down here with only 20 degrees here, right? Because this is your 70 degrees. So this is celestial equator. Okay? Now, what is the declination of the sun on June the 21st? It always is, no matter where you are. Declination of the sun, June 21st? Say again? 23 and a half degrees. So the sun is another 23 and a half degrees above the celestial equator. 23 degrees, 30 minutes. Okay? So here's the sun on June 21st. Oh, I put a star. Here's the sun, not a star. Okay. Sun on June 21st. Okay? Now, what is the number of daylight hours then? Okay? Now, Altegard, Norway. Oh, man, I'm stiff. All right. Here's Altegard, Norway, somewhere right up here. Okay? Just about as far north as you can get in Norway. Guess what circle is above? The Arctic Circle. And guess what? On June 21st, what happens to the sun above the Arctic Circle? It never sets. So how many hours of daylight do you have? 24. How many hours of darkness do you have? 0. You got it. So that one was pretty easy, wasn't it? Okay? Now we're going to go to the 21st of December. What's the declination of the sun on the 21st of December? Negative 23 and a half degrees. Okay, or negative 23:30. Well, where is that? Here's the celestial equator. The sun is down here somewhere, which is below the horizon. What does that mean? It never rises. So how many hours of daylight you have? 0. How many hours of darkness you have? 24. I don't want to be there. Okay? On March 21st, what's the declination of the sun? 0 degrees. And how many hours of daylight do you have? 12 and 12. All right. Equal day, equal night. All right. Now we're going to move to Quito, Ecuador. Okay, Quito, Ecuador right there on the equator. What is the declination of the sun on June 21st? 23.5 degrees north. How many hours of daylight and darkness do you have at Quito, Ecuador? 12 and 12, because it's on the equator. Equal, equal. Equal day, equal night again. How about December 21st? What's the declination of the sun? Negative 23.5. But how many hours of daylight and darkness you have? 12 and 12. And March 21st, declination of the sun? 0 degrees. And how many hours of daylight and darkness? 12 and 12. Man, that was easy, wasn't it? Actually, it must have been 5 or 6 years ago, I had a student from Kenya who was in this class. Okay? And here's Kenya right there, and she lived awfully close to the equator. And that's the thing she had most confusion with when she moved here to the U.S. She thought all days, no matter what time of year, you had 12 hours of daylight and 12 hours of darkness, because she lived on the equator. When she moved here to Alabama, the days were longer in the summer, shorter in the winter. It made no sense to her until she took the sports report. And then everything made sense, right? No. But she was so surprised, she thought all days everywhere were 12 and 12. They're not. Only on the equator. All right. What time?
5:41.
41. Okay, let's turn back one page again to 365, and let's do number 11. What we just did was number 10. We did that on the table. Let's do number 11. No, we didn't do 11. We only did 10. 10, we answered the question, does the sun rise exactly east? No, it rises north of east. And then we did the table 1, and we just did those 9 pieces there. So let's now go to number 11. Calculate the altitude of the sun, that's the degrees above the horizon, in degrees over the southern horizon at noon on June 21st for an observer at latitude 40 degrees north. So this time let's erase what we've got here. Let's erase what we've got here. Okay. We'll keep that. We'll erase this and that. Okay, erase that and that. And we'll erase these down here too. Okay. All right. Let's get back where we were. I've lost it. There it is. 40 degrees north. Okay. That means, let me get my pen back. Okay. If this is 40 degrees north, that means that is 40 degrees north. Okay. And this is the celestial equator. Right? 40 degrees below your zenith. Okay. Calculate the altitude of the sun in degrees over the southern horizon. Remember, this is southern horizon. This is northern horizon. Okay. On June 21st for an observer there. What is the declination of the sun on June 21st? 23.5 degrees. So that's going to be something like, I probably did too much. Slow down. No, that's about right. Okay. It's just not very pretty. Okay. All right. So this is another 23 degrees, 30 minutes north of the celestial equator. That's the declination of the sun on June 21st. So the question is, what is the angle above the southern horizon? Well, if this was 40, what is this angle here? 50. And then you take the 50 and add 2330 to it, and what do you get? 73 degrees, 30 minutes. Or 73.5 degrees north. Okay? Got it? Now let's repeat that. Any questions? It's time? Let's just get number 12 done so we don't forget it. Let's do on December 21st. This is June 21st. Where is the sun on December 21st? Negative 23. So that's 23 degrees and a half degrees, 23 degrees, 30 minutes south of celestial equator. Okay? So if this is 50 here, we do 50 degrees, that's where the celestial equator is, and now we subtract, only let's not do 50, let's do 49 degrees. This just makes your calculation easier. That 50 would be 49 degrees, 60 minutes, and subtract from that 23 degrees, 30 minutes, and what do you get? 20 what? 26 degrees, 30 minutes. So that's the altitude of the sun over the southern horizon on December the 21st. Okay, so here's what, No, wait. Okay, what we're going to do next time, we still got to do 13, 14, 15, 16, 17. They're not going to take long. So the first thing we do on Thursday, we'll finish the lab. Okay? Then we'll get started in chapter 15. Say again? On Thursday. Day after tomorrow.
Okay.
We'll start by finishing the lab. We only got a few questions. Then we will start chapter 15, and we'll go until 5:15. At 5:15, I'll give you the test for chapter 14, if you choose to take it. Okay?
You're going to give a test Thursday?
The test on chapter 14 is Thursday. But if you don't feel like you're ready, say again?
Based on the PowerPoint.
Based on the PowerPoint and the reading and what we've said in class. All that. Okay. So it'll be up to you whether you want to take it or not. If you want to wait till you get your books, you can do that. Oh, I thought you were leaving me a gift. Okay. All right, good deal. Have a good evening. We'll see you on Thursday.
Okay. Thank you so much.